those of you who don't know, I will give a short intro about him. So, Professor Amit Kumar, he did his PhD degree from Cornell University. He completed there in 2002. He then served as a member of technical staff at Bell Labs. He then joined IIT Delhi as a faculty member in 2003. Currently, he serves as the Jaspinder and Kavinder Chadda Chair Professor at IIT Delhi Department. He works in the area of optimization and online algorithms. So let's begin.
Okay, thank you. Okay, so this is the second talk by me in the series. So last time we talked about approximation algorithms. This time we will talk about what is called online algorithms. So as you will see, the model is different, and so the issues will also be different. So we'll talk about, this is of course a very general area, and all the problems that you have seen so far, for each of those problems you can have a version here in this model. Okay, so what is the model? The model is that, unlike the problems that you have studied so far, where you are given an input, given an out, and specification, you want to produce an output, and the challenge there is to have efficient algorithms. Right? You can always solve it in, let's say, exponential amount of time, but then the challenge was to find an efficient algorithm. Here the challenge is something else. Here the challenge is that the input is going to arrive over time, so you don't get to see the entire input. And so the challenge is, how do you get around this sort of uncertainty where you don't know what's going to happen in the future. Now there are many ways of modeling this. This is one of the ways. If you talk to people in other areas, they will have other ways of doing this. But the model here is that the input, let's call input arrives over time. Okay, so the input is going to arrive over time. Okay, so take any problem that you can think of, and we'll do some examples. So input is going to arrive over time, and so let's say at time 1 sigma 1 arrives, at time 2 sigma 2 arrives, at time sigma t arrives, and so on. Okay, and it goes on for a long period of time. Okay, and what you want to do is, if the algorithm knew the entire input, it would have constructed a solution for your problem. But that's not what we want. We want that at every point of time t, when you have seen this piece of the input, you should have constructed a solution for this part. Okay, so at every time t, you want to maintain a solution for this part of the input. Whatever has arrived so far, for that you should have maintained a solution. Okay, so have a solution for, I'm going to call it sigma less than or equal to t, which means that sigma 1 up to sigma t. Okay. So whatever decisions you have taken so far, can't change that. This keeps on going. So, and the fact that you didn't know the entire, maybe if you knew that this is what the input is going to look like, you would have done something else. But here, this is how you have to be here. So whatever decisions you have taken, that's done, and you just have to build on it. Okay. So this is online algorithm. Note that I have not said anything about efficiency here. So if you want, you can take exponential amount of time. The model allows you that. But of course, in practice, if you're going to implement this, you better not do that. Okay. But there's nothing as such which says that it has to be efficient. And you can imagine where it gets used. It gets used everywhere, because in any practical setting, the input is going to arrive over time. You're not going to know the entire input in advance. So as time progresses, you learn more, you get to see other parts of the input. Okay. So this is online algorithm. How do you say how good it is? Just like we had the notion of approximation algorithm, here also I will have a notion of approximation ratio, but we call it comparative ratio. Okay, so we call it comparative ratio. So it's exactly the analog of approximation ratio. Okay, and I'm going to assume that you are minimizing something. If you are maximizing something, whatever you are building, there is an objective function there. For example, last time we talked about facility location. So what would be the analog of facility location here? Analog would be that you don't get to see the demands upfront, but they arrive over time. And as they arrive, you have to take decisions. Whichever facilities you have opened, they will stay open, but you can open more. Okay, something like that. Okay, so so the ratio is comparative ratio, which says that this is the cost of the algorithm, right? So the cost of the algorithm on some input, right? When it has seen some input sigma 1 plus sigma t. Okay, so this is how much it incurs when it has seen some piece here by the cost of the best solution, cost of the optimal solution for sigma 1 or 2. So I'm going to say optimal offline. Offline means that this thing gets to see everything. Okay, so it's way more powerful. Optimal offline algorithm for sigma 1 up to sigma t, and I'm going to take the maximum over all possible inputs. Okay, so this is a ratio. It's always going to be greater than 1 or at least 1, because whatever I do, I cannot beat the optimal algorithm. So my hope is that I want to bring this number as close to 1 as possible. So with that background, any questions? Is the model clear? So it will get clearer as we do some examples. So the first example I want to do is the most basic one. It's called ski rental. Sometimes people call it rent or buy. And it underlies the sort of uncertainty which is there in many such problems. So even though you may not be solving this exactly, but in many situations, many online algorithms have this as some sort of component inside.
So in the comparative ratio, it seems like the ratio depends upon the value of t, small t that you're taking. So
good. So it better not depend on t. Yeah, you're right. So there could be various parameters here. It could depend on t. It could depend on some other parameter n. Right. So we will see what those could be. In general, it could be, for example, log of t, but that's not desirable. It's not desirable because t could be infinite. So then that's not good. But that's a very good question. So in most on most applications, you would imagine that this t is going to infinity. And this is something I'll come back to. Okay, so let's begin with the simplest one, rent or buy or ski rental. So the idea is the following, that ski equipment is very expensive and it costs you B amount of money to buy it. Okay, so the cost of buying ski. But if you rent it, it's going to cost you much less. It's going to cost you 1 unit of money. Rental cost per day. Now the issue is I don't know how long it is going to snow. So let's imagine the input is like this. Of course, this is just a toy problem. That on each day it will either snow or it does not snow. If it snows, then you can use your ski. So, but the input is going to look like snow, 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 and after a day it will just stop snowing, and then it will never snow again. So that's how it's going to look like. So the input is, of course, that's a oversimplification, but input is going to look like that. There's an unknown time t, and then till day t, it will ski, and then after that report, right? So till day number t, it snows, and of course, assumption is that you want to ski every day. So till it snows. So till day t it snows, and then it does not. Okay. So the question is, should I buy the ski or should I just keep renting it every day? So what's my best strategy? So let's first understand, if you knew the input in advance, if you knew the parameter t, what would you have done?
If t is greater than t,
Yes, right. So if t is bigger than right, so go good. So the optimal solution, offline solution, which knows the input, is that if you know t, right? So if you know t, so if t is at least b, then just buy it, or if t is less than b, just keep renting. So it's min of t and b. So that's the optimum. Whichever is smaller, you pay that much. Right. Now the question is, I don't know this. So what do you think I should do? What's an online algorithm? So every day it decides before before the day starts, I have to figure out whether I'm going to rent today or buy, and then I get to see what outcome is. So or maybe you get to see that whether it's snowing or not, but then you have to decide. Okay, so every time t the input arrives, it says you get to see whether it's snowing or not, let's say, and then you decide. So what would you do?
So you keep renting until some point that you think.
Okay, so keep any strategy, right? Any algorithm will be like keep renting till some day, and then you say that enough is enough, I'm going to buy it, right? That's what anybody will do, right? So any strategy, right? So any algorithm, right? So any algorithm, okay. Any deterministic algorithm, any algorithm which is deterministic. Okay, I'll say what deterministic means, but any algorithm is for now will be like keep renting till some day t, keep renting till, let's say we have used b, so let's use some other letter, keep renting till day x, and after that y. Any algorithm is going to look like that. Now suppose you knew this algorithm, okay? Now okay, so let's try to first figure out what x should be. What do you think x should be? So if b is very large, it's very expensive, what do you think your x should be? Should be also larger, right? If b is very small, it should be small. So what do you think we should set x as? B by 2? Let's just B. Okay, good. So let's just set it to B. So we just, as you're suggesting, let's set x to B. And then let's see how good or bad it is. So now what do I have to prove? I have to prove that take any input, see how much this costs and this much cost, and take the ratio. Now there are only two cases, right? So let's look at any input where it snows for t days and t is less than b. Okay. So if t is less than b, what is the optimum? Optimum is t. How much will I cost? I will also cost t, so my ratio is 1. Okay? So this case comparative ratio, I'm going to call it CR, is 1. So let's see what happens when it snows for more than b days. Okay? In this case, what is the optimum? It will say b. How much do I incur? 2b. Right? Because why? Because for the first b days I'm going to keep on renting, and then I'm going to buy that also. So it's 2b. So comparative ratio is 2b over b, which is 2. So no matter what happens, you will never overpay than twice the best optimum algorithm which knew the value of t. Can I do better? So instead of using b, suppose I had used some other x here. Do you think I can do better? So for example, suppose I had said that that number x was smaller. So I'm going to rent for b by 2 days. Do you think it will be better? Or do you think there's an input where even that can be So suppose I said that no, b is too much, maybe I should just stop at b by 2. What do you think will happen? When you stop at b by 2, let me give you an input which is just beyond b by 2. B by 2 plus 1. So how much will you pay? 3b by 2. Optimum is b by 2, ratio is 3, it's even worse. Okay? So convince yourself as an exercise that no matter what you do, if you choose your x to be something else than b, you cannot get better than 2. So 2 is in some sense the right balance. Any algorithm will have to incur, right? So any algorithm will have computed ratio at least 2. Because if your x is less than b, I can make you still pay more. If your x is bigger than b, then again it's a bad strategy. You can convince yourself. Okay? So this ratio will be minimized at 2. So the right value of x is equal to b. So we have a 2 competitive, right? So the way people say this is you have a 2 competitive algorithm for ski rental, and that is optimum. So 2 competitive. And it is best possible. Okay, so let's think why I couldn't do better. The reason was that if somebody knows what my, so it's like a game being played. You are an algorithm, you are an online algorithm, and you have a strategy. You have a strategy that I will rent for X days and then I'll stop renting. And what I'm saying is that if I know what your X is, I'm going to design an input which will be very bad for you. So for example, if you said that I'm going to rent for B by 2 days, I will design that input for you, right? B by 2 plus 1. So if I know what you're doing, then I can design an input, right? Because this ratio is that if you know what the algorithm is, so cost of the algorithm on this input is max possible. So I'll design the worst possible input for you and I'll make you pay a lot. So in this case, the inherent assumption is that the adversary or whoever is designing this input for you knows what you're doing. And why can I do that? Because I can look at your code. Let's say it's an algorithm. I can look at that code. I can see what it is doing. And so then I can design the best. I can know exactly what it is going to do when this input arrives. And so I can design worst possible input for it. Okay? But this assumption only holds if your algorithm is deterministic. What if I were tossing coins? So how would, right, so I should have qualified this. It is best possible for any deterministic, right, only if your algorithm is deterministic. What if my algorithm is randomized? It uses coin toss. Because then you will be confused that what should be the best possible or the worst possible input for me. Okay, so let me give an example. So if the algorithm is randomized, how do I change this definition? The only change I make is that I put an expectation here. Okay, the expected cost incurred by the algorithm by that ratio. Okay, so far so good. So how would a randomized strategy look like? For example, a randomized strategy can say that with half probability I'll wait till day B, with half probability I'll wait till day B by 2. I can do that. Okay, so let's see. And let's see if we can analyze this algorithm. Right? So the algorithm now is randomized. With half probability, you buy on day B, and with half probability, you buy on day B. Okay, that's an algorithm. Okay. And what do I need to show? So this is your time horizon, and you say that on day B by 2, I'm going to toss a coin. If it's heads, then I'll buy it on that day. Otherwise, I'm just going to wait till day B, and I'll buy it on that day. Okay, so that's some sort of trade-off that I'm trying to achieve. Now, what do I have to do? How do I analyze this? I want to say that I look at all possible inputs. Inputs will be like they keep on going, snowing till some point and then stop snowing. and on each of those days I need to calculate this ratio and see how bad this ratio can get. Now you can imagine that if this input only goes till here, then I will be as good as anybody else. So the only sort of inputs, convince yourself, I have to try is either when the input ends right after day b by 2 or it ends right after b. Everything else will only be somewhat better for me, because if you take your thing to this point, I will either be renting all the way till then, which is okay, or I would have already bought it, then in this period I will not pay anything. So even though I am not making it very precise, the only two inputs I have to worry about are these two. And if I can look at this ratio for these two inputs, for all other inputs the ratio will only be better. Okay, so again I am not giving you the complete idea, but I am just going to analyze this algorithm on just these two kinds of inputs. The rest will only be better. And so let's see what happens to the algorithm. So if in the first input, where let's say it snows till day b by 2, the optimum solution, right? So let's look at the first input where it snows till day b by 2. What is the optimum solution? B by 2. What is my algorithm going to incur? My algorithm will say that with probability half, I would have rented till b, in which case I will incur b by 2. With probability half, I would have bought at day b by 2, so I would have paid how much? b by 2 plus b, 3b by 2. So if you look at the sum, this is b, right? So again the ratio is 2. So it's not helping. Now if you look at the other input, there the ratio is slightly better. Here optimum is b. Let's see how much I incur. With probability half, I would have bought here, so I would have paid how much? 3b by 2. With probability half, I would have bought here, in which case I would have paid 2b. And this is less than 2b. Why is it less than 2b? Because this is 2b and this is less than 2b. But on all inputs I am not doing. So what is the comparative ratio of this algorithm? It is still 2, because on some input it is twice the optimum. But now you can imagine that let's have slightly, maybe this was a stroke of luck. So maybe I say, maybe not b by 2, but maybe you delayed further. Okay. So now you can ask, let's say I till day alpha b, I keep on renting. Okay. And after that I just buy. So think of alpha as 0.9 now. So till 0.9b I rent, and the other strategy is till day b I rent. And if you do this calculation again, you will see that the comparative ratio will be less than 2. Okay, so let's see why. Let's quickly do this. Okay, so you will tell me what are the two values here. Let's do this quickly. So if it snows till day alpha b, where alpha is less than 1, I'm trying to figure out what's the best alpha. What's the optimal solution? Alpha b, right? You rent till alpha b. How much will I pay? I'll keep paying alpha b here, but then I'll also buy it. So alpha b plus b. Correct? And about this other one, optimum solution is b, but I will, with half probability I'll do this, with half probability I'll pay alpha. Correct? With half probability I would have bought here, with half probability I'll go all the way. If I buy at alpha b, I'll pay alpha b plus b. So far so good? Stop me if I'm going too fast. So this is alpha by 2 plus half alpha plus, sorry. Yeah, good. Question? So what is the ratio here? The ratio is 1 plus 1 by 2 alpha. Okay, quickly doing it for you. You can check everything. And if it snows till day B, how much will you pay? Well, optimum is B, but with probability half, I would again pay alpha B plus B, just like this, but with probability half, I'll pay 2B. So this, if you do the calculation, it is B plus 3B by 2 plus half alpha times B. So here competitive ratio is 3 by 2 plus half times alpha. And if you chose alpha as half, what was happening was this was becoming 2, this was the. So you want to balance these two things. And if you pick the right value of alpha, you make them equal. And so if you pick your alpha to be something like root 5 minus 1 by 2, this ratio, both of these will be equal to something like 1.8. Okay? So you can do better than that. So you can see what's going on, right? You're hedging your bets. If you rented all the way till B, then there is a bad input for you. What's the bad input? That keep snowing till slightly beyond B. So to hedge against that, you will say that okay, if that's the input that it keeps snowing till that point, I should have maybe bought earlier. So that's why I'm going to say that I keep some probability that I'm going to buy somewhere here. And that kind of helps you. Now you can imagine why only this strategy, why not something more complicated? Maybe I say that with probability 1 by 3 by here, with probability 1 by 3 by here, with probability 1 by 3 by here, or some other complicated distribution. Okay. So you can do that. You can do that calculation and figure out what's the optimal strategy. That's the calculation we can do. But I'm not doing it because it's not very enlightening for us right now. You get a 1.8 there. If you work with a more complex distribution, you will be able to get E over E minus 1, which is like 1.6. Okay, so you can bring it down from 2 to about 1.6.
What happens if we buy with, say, uniform 1 by B probability on each day?
Sorry?
With like 1 by B probability we buy on any random day from 1
So you can do that calculation, it won't be very good. Right? You won't. So this has to be some other kind of exponentially decreasing. So this will be somewhat like, distribution will be like high here and will keep on going down like that. So it won't be a uniform distribution. Okay? Yeah, but you can do those calculations. Those are good exercises to do. Okay. And try to figure out what is the best distribution. But the role of randomness is clear, that what it does is that you cannot now say that your algorithm will be bad on this particular input, because it doesn't really know, the adversary doesn't really know what I'm going to do, what my coin tosses are going to be. It doesn't know whether I'm going to buy here or here. Okay. So that allows you to save on that competitive ratio. Okay, so we will come back to randomization if we have time, otherwise this is a very important aspect of online algorithms. Many algorithms, many problems, you can show that you cannot do much if you are only doing deterministic, but if you allow it to toss coins, then there is a dramatic improvement in the competitive ratio. Okay, so let's do another problem. So what I want to do is I want to talk about one or two techniques that people use. There are two main techniques. One is called potential functions, and the other is called, again, we go back to linear programming. So I will not show you the linear program, but I will show you what it means to use a linear program. So,
So I have a question. So in these sort of examples like ski rental problems, when we use competitive ratio, the max in the definition of the competitive ratio, so it doesn't capture the whole picture, because it kind of assumes that the input is adversarial. But if the input, like in the case of snowing, the input is kind of random, it is not adversarial.
that's a very good point. So in this model we are assuming, just like worst case analysis, right? When you look at the running time of an algorithm, why do you look at worst case?
Exactly.
You can, maybe that input will never arrive, right?
Right, so what if we do some sort of a average case analysis of this?
Yeah, average case can be done. So why, for example, again going back to running time, we can do average case, but why don't we do average case, right? The reason is, there are two reasons. One is that average case would mean that you have to have, you assume the probability distribution from which they are coming. That is known to you. For different distributions, the performance could be different.
Right.
So then you have to make a list of, if this is the distribution, then this is how it will look like and so on. But you were right. In online algorithms, there are models like that, where they say that the input arrives according to some distribution. Okay, let's say with probability p, it will either stop snowing from tomorrow or not, right? Something like that, and you know what this probability p is, right? Or if you're doing machine learning, you try to learn what this probability p is, right?
Right. So suppose in a sort of a practical scenario where if we actually think of this key rental problem, so there's some sort of a prior information about the weather.
And then you want to include that in your calculations, right? So I can give you pointers to more recent sort of models. So this is something only people have started looking now, where where the input is is coming from a distribution. There is stochastic assumptions about the input, or you're trying to learn these things. So, but the most basic model here, just like worst case, when you look about worst case, is I'm looking at the worst possible. Okay. So second one is a very classical paper, which started many of the which underlies many of the other subsequent algorithms, because it introduced this idea of potential function. How many of you have seen potential functions in other data structures? Where have you seen potential functions?
There's this analysis which is amortized analysis.
Amortized analysis. Very good. Amortized. Right? You have seen potential function. So I want to show you potential function here also. So this is called list update problem. Now, list update is the following, that at every time, so you are maintaining a list of n elements. Okay, so you're maintaining a list, linked list, right? Think of linked list. Okay, so this is some list that you're maintaining. Now, what's going to happen is that at every time, the input is going to say that I want to access this element. Okay, so name of one of these elements. Okay, so E1 up to En may not be in that order, right? So E5, E3 in some order, E7, and so at each time t, the request is some element Et. And so what you do is you go here and you scan, and when you see that element, then you get all the information about that element. And so the running time would be that if this element is x positions from the beginning, you incur x amount of time. Okay, because scanning a list takes time. But you are also allowed to update your list. Okay, so you are also allowed to change the list. So for example, if you see that some element is getting accessed many times, you would like to move it to the front. Okay. So the model is that cost is x units to access an element at position x, at position x from front, okay, that's one thing. And the only way, you can also change this list, and the power I'm going to allow you is you can swap two elements. Okay, that's the only thing you can do. This is very flexible. Even though I'm saying like this, you can change it model also, but the power, you can interchange any two elements. But let's say that you're only allowed to swap the two elements, two adjacent elements. Okay, so I'm allowing you to swap two adjacent elements. Okay, so swapping two adjacent elements costs 1 unit. Okay, you can change the model. You can say you can swap any two and all that. So really like a linked list. So if you want to move something forward, you can swap it with the previous one, so on. Now, even offline is not clear now, right? What would you do? Right? Because imagine that offline algorithm, it knows the entire input. Now, it will again have to do something clever, but it sees what is going to happen. If it sees that something is going to get accessed very often, it will try to move it to the front. Okay. So unlike the ski rental, here I don't even know what the offline optimum is. Now, if the offline were not allowed to manipulate the list, then it's very easy.
So for the offline algorithm, we can use rearrangement inequality and put the ones which are most accessed right at the beginning?
No, because let's say you're saying that the one which is accessed most frequently should be at the very front, but that's assuming that the offline cannot change the list. Offline is also allowed to change the list. So maybe the element, let's say element 1 is going to be accessed millions of times, but that's not going to happen now. Maybe you know, 1,000 time units from now onwards. For the first initial 1,000 cycles, element 1 is not accessed. So why do you want to put it at the front? Okay. So I'm allowed to change my list, right? Let's say I am going to access element number 2 for the first 1,000 units, and then you're going to access 1 forever. So you should put 2 at the front and then bring 1 at the front, right? So yeah, you're right. If you were not manipulating that list, if your list was static, then I would arrange by frequencies. Good. So it's not clear, right? I mean, what the offline solution is. So unlike the previous problem where you could write down what the optimum is, here it's not clear.
We can consider it as an OS problem using cache replacement policies. The optimal, there's an algorithm for that. It looks at the following the incoming requests.
Yeah, so I don't know what the optimum is, right? I'll have to. I don't know how you'll prove it. But the point is, it's not. I mean, it's not obvious, right? Unlike rental, where you could maybe you can use the dynamic programming to solve it or something, right? It's not completely clear to me how you will find the offline optimum. But the way I'm going to do it is that you don't have to. Okay. So and that's the clever idea about this this technique.
So for offline algorithms, why don't we just sort the elements and then like
Sort according to what?
according to the size of the, for example, like the lexical ordering.
Or let's say even up to 1 to n. But at every time t, I'm not going to. Okay, so maybe this is confusing. At every time t, some e sigma t is accessed. So it's not like at time t, at time 1 1, at time 2 2. It's not like that, right?
So even then, like even if they are like E1, E2, En all are numbers, and if you just order them, then the cost like accessing an element which is at position x, now it only costs 1 unit because you know exactly the.
So suppose suppose let's say you're inserting like elements are like this, right? And E7 is at the very end. Now if I access E7, it will cost you a lot of money to go all the way till there. Now why can't adversary also fool us here, right? Access the guy which is at the very end, always. That seems like if I know what the algorithm is doing, let's just do that all the time. But turns out if you do that, then you yourself will incur a lot of cost. Right? So it's not like ski rental, but you will see. Problem is that I don't even know exactly how the optimum looks like. Okay, so this was a very, very nice paper, highly cited paper. This was Slater and Tarjan. I think so. They showed that the MTF heuristic is to, okay, for the model that we have, it will be 4 competitive. Okay. What is MTF? MTF is move to front. It says that anytime some element is accessed, move it to the front. Okay, and just always do that. Algorithm is clear. So it's very immersive, right? So how do you analyze this? Yeah, you have a question.
Yeah. So in the swapping cost, like you're swapping any two elements with the cost of 1.
Any two adjacent ones.
Any two adjacent ones, but the adjacent could be far away. So do I need to go there first and then?
Yeah, so all those models are there, you're right. So I'm allowing the algorithm will never do that kind of thing, you see. That it won't say that the request is at position 10 and swap the 99th and the 100th element. It won't do that kind of thing. But I'm allowing you the power. So it makes only the offline stronger, but the optimum algorithm is not going to do that kind of crazy.
Okay, so in this model you can swap anywhere with.
Yeah, so I'm allowing you the power, but I'm not going to use such things. But I'm going to allow the offline algorithm with which I'm comparing with this power, just to simplify it. Good question. Okay. So good. Now, how do I analyze this algorithm, right? Because it's very crazy, right? And the idea is to use a potential function because I don't know how the algorithm will look like. See, ideally would want that I would want that cost of the algorithm at time t is less than or equal to 4 times the cost of the optimum at time t.
So just to make sure, the online algorithm that you are inventing, I mean, if that wants to put element 10 at location 1, it won't do like 9 successive swaps. Right?
Yeah, so how much time will it take? So if something is at position x, how much time will my algorithm take? It has to access that x units, then it has to bring it to the front, another x, the 2x. Okay, so this I want to prove is less than or equal to 4 times the cost of the optimum at time t. So if I can prove this, then I am done because I'll just sum this over all time t. But this cannot be shown. Why? Because maybe the element that is I am accessing at time t is very far away in my list. In the optimum sets, it's maybe at the very front. So how can I say that this would happen? This is something I cannot prove. Okay. So what I do is I add another term here, which is trying to balance this out. It's going to balance this thing out in the sense that if my solution and the optimum solution, they look very different, then this is somehow going to balance it out. Okay. So now this will look a bit strange if you have not seen potential function, but I'm going to define some potential function phi. So right now just think of it as some measure of how different my solution looks from the optimum solution. It's a measure of how different we are. Okay. And this quantity will always be non-negative. Okay. And what I will show is that the cost of my solution at time t plus the change here, okay, plus phi at time t plus 1 minus phi at time t, delta phi, okay, this will be approx this. So what that says is that if this is much more than this quantity, then after I incur this extra huge amount of cost, this guy will go down. Okay, we will see how.
Sir, could you define phi t? What do you mean by that?
So phi, it's something that I'm inventing, right? It's not something as part of my input specification. So and this is the exact definition I'll show you in a minute. Okay, but this is what I'm going to prove. Okay, so right now think of phi as some crazy thing that I've invented, and I'm going to prove this to you.
And this delta is non-negative? This delta, this difference, phi t minus 1 minus phi t, this difference?
Yeah. So this would be negative if this is very large, so that this cancels with this. Okay. Have you seen this kind of thing before? Okay. So why is this okay? Now let's add it up over all time t. What will happen to this term when you add it over all time t? It will keep on cancelling. Keep on cancelling. Right? So what will you get? So if you sum over all time t, what do I get? On the left side, total cost. Sum over t, cost of algorithm at time t. What happens to this? What survives? What doesn't get cancelled? Phi at time t minus phi. Yeah, right? So phi at time t minus phi at time 0. Phi of 0, I'll set it to be equal to 0. Okay. And phi of t is, remember, is positive. So this quantity is less than or equal to 4 times sum over t cost of opt at time t. Okay, and because this is positive and this is 0, this I can get rid of this. This is still okay. So that's my idea. So this is just a stopgap kind of thing, which is helping me. Yeah, questions.
Just proving that the sum over all t is lesser than or equal to 4, that is not enough. Right?
Why?
For every small t, this this the ratio is lesser than.
Yeah. So let's say I'm trying to argue till some time capital T, right? So right, I'm trying to show that till sigma 1 to sigma t, if you go all the way till here, my cost is at most 4 times cost of opt here. And this t I can keep changing, right? If it is longer, then I can stop any time. Right? See, what do I have to prove? I have to prove that my total cost till some prefix of this, right? Is that what is worried about? But that is my prefix, right?
Okay. So we are just concerned with the total cost over.
Overall some time horizon from. So when I said t, what I meant was t is equal to 1 to some limit here. Right?
Not the individual cost at that stage. That is not.
Right, I mean, because that's what I want to say, right? I mean, for any time t, the total that you have incurred till this time. Okay. So what is the potential? What is phi here? So let me show you how this works. And many algorithms came after this, which use this idea of potential function. And so the art lies in figuring out what this potential function is. And in this case, the potential function was how different the two lists appear. So remember, each list is a permutation. Okay, so each list is a permutation. So phi at time t is the number of inversions in the two. Okay, so number of inversions. I'll say what this is in number of inversions between the two lists. So between the algorithms list and optimum list. Okay. What is inversion? Inversion is a pair of elements which appear in the wrong order in the two. The order in which they appear in one is different from which they appear in the other. So for example, an element ei, ej, suppose it appears like this in my list, but it appears in the other order in the optimum list. Okay? Yes?
So, but this does not check how far was that from the.
This is not. This is what it is. This is what I have invented. I mean, it's my definition, right? I'll just have to prove this.
But just a follow up, the cost we incur for swapping the inputs is 2x, right? But in the optimum function we are defining, so both of them are different. So how do we compare them?
We'll see. Okay. All right. So how big can this be? Could be n square. Every pair is out of order. So now I have to just verify this thing for you. Okay. And the way I'm going to verify is in two steps. First of all, the algorithm will go and access, and then come back and bring it to the front. Optimum is just going to go and access that element. I'll compare the two, and then after that, optimum may also swap. If optimum swaps two things, I'll show you that this inequality still holds. Okay. So for the first part of the argument, I'm going to assume that the optimum just goes there and accesses that element, does not do any swaps. Okay, and then I'll allow it to swap. Okay. Is clear? Okay. So let's see. So this is my list, and the element that you're accessing, let's say, is sitting here. Let's say k units away from the front. This is the element that is getting accessed. So this is the algorithms list. And this is the optimum list, right? And the other, maybe it's closer, I don't care, I don't know. So maybe it's sitting here. Okay. So maybe it is sitting closer, maybe that's sitting r steps away. Okay?
So just one clarification. By number of inversions, we mean the number of adjacent swaps we need to make to go.
No, number inversion is just a function of the permutation. Right? Suppose I give you two orderings of n numbers.
Right.
Then what is an inversion? An inversion is that for every pair of elements, you check whether they are in the same relative order in the two lists or they are in different orders.
Right.
So for every n choose 2 pair, you check whether this I comma j, if it appears I appears before j here and I appears before j there also, it's not an inversion. So if they appear in the wrong opposite order, then that's an inversion. So given two orderings, I can just compute this, right, for every pair. Every n choose two pair, check whether they match or they don't match. And now just count how many out of order pairs are there. Okay, so this is just a function of these two permutations. Okay, good. So what is the cost of my algorithm? You have already mentioned this is 2k. What is the cost of optimum? This is r, because it has to go and access. So it will incur r definitely. It may incur more if it swaps. We'll see that about. That we'll just keep that on hold for now. So now I have to make sure that the change in potential accounts for this extra, because k could have been much larger than r. And now of course I have to worry about the other thing also. Maybe k was less than r, but this thing went up. So shouldn't go too much up. Okay, so now there are two kinds of elements here. There are some elements here. So this, let's call this element E, which is being accessed. E is accessed. Now there will be some elements here which will appear before E and then appear before E here also. Right? So there are some guys here which appear here and which appear here also. And then there are some elements here which will appear here, but they may appear on the other side. Correct? So let's give it some name. Okay, so K1 are the elements here which appear before E in opt also. Okay, so K1 appear before E in both lists. In both. Okay, and K2 is appear before E in algorithm, but after E in optimum. Okay, so there are two kinds of guys here. What can I say about K1? If all the K1 guys are also appearing here, K1 cannot be more than R. So one thing I definitely know is that K1 is less than equal to R. What else? K1 plus K2 is equal to K. That's also clear because, I mean, there are only two kinds of elements. Now, when you move this element from here to here, what happens to the potential? How many inversions are affected? Now note that I am not changing order of any two elements except those with E. Those are the only guys which are getting affected. Any two other pairs are not getting affected. Their relative ordering is not getting affected. So the only thing I have to worry about is E with respect to these guys and E with respect to these guys. That's all.
Only K2 many will affect.
So which one do you think? So okay, how many new inversions will be created? The inversions which did not exist earlier but now are going to get created. K1, right? Because K1 was before in both. Now you are going to move E out here, so then these guys are going to appear after, whereas they are appearing before. So you are going to add K1. But K1 is not much though, K1 is only R. But what happens to K2? K2 are going to get fixed. So how much is this term here? It is K1 minus K2. Correct? And now that you see that I should have been careful, so I should have put it twice here. Because I want it to cancel with that, so I'll just put twice here. Okay. Does not matter. So this becomes twice of this. Okay? So far so good? So 2k, so when you add them up, what do you get? Remember k is equal to k1 plus k2, so 2k1 plus 2k2. So when you add them up, k2 cancels out. Remember, if k is much bigger than r, it's because of k2. K1 is at most r. So what do I get? I 2k1, 4k1, and this cancels out. So this is only 4k1, whereas here you have r. R could be at least k1, and I have factor 4 sitting here. So it's okay. Alright. So, so far so good. Now what happens when, so this is done. Now what happens when optimum switches to guys? Now when it switches to things, its cost goes up by 4. I'm not doing anything. This is 0. Now I have to make sure that this does not go up too much. How much will this go up? Well, we are only making one swap. So the number of inversions can only go up by 1 only. So this could have been at most 1. There is a factor 2 here, so it could have been at most 2. So it's still okay. Okay. So yeah.
Could you repeat the?
Okay. So which parts? This first part is okay. So there are 2 steps, right? One is you are accessing and moving it to the front. So now I have done this calculation here. It says that the optimum is going to incur R units. Okay. And so this is 4R, and this calculation that you do is also at most 4R. But now remember, I was also allowing the optimum algorithm to switch to things. What about that? So now let's say that the optimum does some swaps, and I'll do this accounting one by one. So each time it does a swap, how much cost I have to check this still holds. Why do I have to check this? Because the list is changing. If the list is changing, this quantity is going to change. Potential is going to change. The moment it changes the order of 2 elements, the ordering changes. So the potential changes. So I have to verify that this holds.
Why is the cost of the optimum at time t equal to R?
Well, what is the optimum? Optimum is first going to access this element, right? And then I'm also allowing it to the power to interchange anything, do any swaps. So that I have not accounted, because if it swaps 2 elements, it incurs some more cost. But then why is that a problem? The problem is that okay, it incurs more cost, but my potential also changes. Because remember, I was counting the number of inversions. So if you change one list, then the number of inversions between that list and my list will change.
Right.
So that also have to check.
Cost of opt at time t is greater than R. It's greater than it.
Right.
Sorry?
Cost of opt at time t is like greater than it or equal to R.
Greater than or equal to R. But remember, see this argument that I did here. It assumed that the optimum is also not changing things around. Because if it were changing things around, then this argument is not correct. Maybe it also moved things around. So then the change in potential will not be just what I did here. So I'm assuming that it is static right now. And then I'll say, okay, let it now change it. And now if it changes, I'll again verify that. Okay. So now if it changes, swaps 2 adjacent elements, this is 4 here. Let's say it swaps just 2 elements, adjacent elements. What happens here? Well, how much will the inversion change? You're only swapping 2 adjacent things. So it can change the number of inversions with any other list by only 1. So this is 1 here. So that's it.
So what about the other case when op takes more time to access? I think that would be very helpful. I was just wondering what about the other case when the op takes more time to access the element?
So it will still be the same, right? We'll check this. When there's nothing here where I assume that R is bigger than Q or R is smaller than Q. Where did I assume that? Okay. So now that I have limited time left, I have a half an hour, so I will talk about the third problem. By the way, okay, so again you can ask whether I can do better than 4. Can I do 2 competitive or 3 competitive? And what would be a randomized algorithm here? What do you think will be a randomized algorithm? Can you think of just like ski rental? What would be a randomized algorithm? A randomized algorithm would be that with half probability I will not move to the front. With half probability I will move to the front. Okay? So I'll toss a coin. If it's heads, I'll move, otherwise I won't. And you can try to analyze. That's one of the exercises. So we'll see what happens there. So yes, again there has been intense sort of activity on this problem, and then there are many more models also. Here I'm assuming that it costs you equal amount of money to swap any 2 things, but maybe there are different rates, So swapping things may not be of equal weight and so on. So people have looked at many models here. Okay, so last problem we will talk about is again going back to set cover. So set cover again, you'll get to see in many versions, many variants, many algorithms. So it's only fair that I do set cover. And this will connect it to linear programming also. So let me define what online set cover means. So online set cover means the following. We are given a set of elements. Okay. So set of elements U. Sorry, it's the other way around. Yeah, so given a set of elements, you don't have to cover everyone. Okay. So you're also given sets, right? Okay. And at each time, so if it were an offline problem, I'll ask you to pick some sets which cover all the elements. But here the problem is different, it's online. So what do you think online would mean here? Sets are given, elements are...
If elements are fixed, that would make more sense.
Well, if elements are fixed and you have to cover everybody, then what's the issue, right? I mean, where's the online?
No, the sets...
See, remember you have to maintain a solution at every time. So even if sets are arriving in the future, if you are time 0, you have to maintain a set cover, then you are killed. I mean, done. What is there to do then? Okay, so the model is the following. Even though elements are there, I'll call elements are dead or alive. Everybody is dead here. Okay. At every time t, one new element will arrive, and we'll say that cover me. And then you have to pick a set if it is not already covered. Okay, so initially no elements. So you can imagine that you don't even know what the elements are. And every time t, a new element shows up. Okay, and other way of thinking is that even though you know what elements are there, you don't have to cover all of them. At every time t, you get to see a new element which you have to make sure is getting covered. Okay, so at every time t, okay, so at every time t, an element et sort of arrives. What does arrives mean? Arrives means that it declares that now I need to be covered. And what you have to do at every time t, your algorithm must make sure that the sets that you have picked cover even up to et. So at every time t, yes, at every time t, maintain a set cover of even up to et. And the assumption is that once you pick a set, you can't get rid of it. So once you take a set, it has to be there with you. You can't say that, oh, I made a bad choice, let me get rid of this and add something else. So once a set is selected, it stays. So question is clear, problem is clear. And what do I want to do? Again, I want to minimize the number of sets. So let me show you an example where again it look like not much can be done.
Sir, do we know all the sets in advance?
Yeah, you know all the sets in advance. You know all the sets in advance. Let's say you also know all the elements in advance.
We know the elements in advance, we don't know the order in which they are.
You don't know the order and you don't know how many of them will come. Right? So if all of them were going to come, maybe you would have done something, but maybe only a subset of them will arrive and then the input ends. Right? Or maybe you don't know the order. You can always assume that they arrive in some order, and you have to be good with respect to every prefix. So I can always assume that it will end at some point of time. Okay, so here's a scenario. One element arrives. Okay, and there are many sets containing it. So you pick one such set. Okay. Because you have no choice, you pick some set. Then another element arrives, which is outside this. Remember, an adversary is giving you this. Another element arrives. Again, you pick some set containing this one, right? Maybe you pick some set like this. Then again, I am an adversary. I will show you an element which is not in these three. Then again, you pick some set. Each time I am going to give you an element which is not there in the sets that you have seen so far. So I can make you pay one at every point of time. But maybe there is a set which contains all the elements. Just because it did not know the future sequence of elements, it never picked it. So the optimum can be 1, and I can make you pay n. Okay. So this is a hopeless scenario in the sense that no matter what you do, there is not much you can do. Okay. So any deterministic algorithm can be made to look very bad, because I can make you pay one every. There are lots of sets, right? There are gazillions of sets containing this element. Okay, this is not. It's not like it's a one cardinality set. There are many other guys sitting also here, but those guys are never going to show up. So you have no clue which ones are going to show up, which ones are not going to show up.
Could you repeat this point?
So at every point of time, no matter what sets you have picked, I'll show you an element which is not there in the previous sets that you have picked. Okay, I can do that, right? So I can make you pay any units. But the optimum will be 1 because there is a set which contains everything. Now you can ask, why didn't I pick that guy? But the point is, you had no clue what is going to arrive. Okay. So
how do we know that there is a set that contains all of these?
Because there are many more elements also, right? So you can imagine that. What will you do? Which set will you pick? So I give you one element. Among all the possible sets, which one will you pick? Will you pick this one? Okay, let's say you pick this one. I'll give you in something other direction. Yeah, I can make you, right? So imagine that the number of sets is very large, right? So I can make you pay a lot here.
Okay. But for the optimal one, how much am I paying?
Optimum knows what the input is.
Right.
So if there is a set which contains all the elements.
But that doesn't necessarily need to be 1 in that case.
It will be 1 here, right? Because I'll just choose this set at the very beginning.
No, but as a kind of set that encompasses the elements I have fed into the algorithm, this sort of set.
So optimum does not mean optimum online. Optimum means that somebody who knew the input sequence.
But
suppose I knew this is what you were going to send. Well, I'll pick this. Yeah, no, that's a valid point. I think the question you're asking is that even optimum will incur a lot if somebody plays this game. But the point is, optimum will not incur a lot because optimum knows what's going to come. Nobody's playing a game with optimum, right?
Right, but what I'm saying is that is it always 1 or not?
No, in this particular setting, what I'm saying is I can design an input. I can design a scenario where optimum is 1, but you will incur a lot.
So by designing a scenario, do you mean that the sets which are present are there in your control?
Yeah, I can give you a set system.
Okay, in that case, yeah.
I can give you a set system.
Right. So in that set system, there's a universal.
That's it.
There.
But I can do it smaller also.
Sure, yeah.
Let's say I gave you all possible subsets. Let's say for the sake of argument.
But what if a set system is not in my control?
No, it is in, I mean, I am the adversary, right? I know what your algorithm is. I'm going to design what the set systems. Okay. So how do you get around this problem? And again, the answer is randomization. Okay. So, for example, what will I do in that setting? So, what does randomization mean? Randomization means that I will do this in 2 steps. So, I'll show you one of the steps. The second step is standard. I'll give you some ideas. So, let's say that at each time t, I am not required to maintain a set cover, but a fractional set cover. What does fractional set cover mean? It means that I am going to give you, you may have seen the linear program for set cover. What is the linear program for set cover? What are the variables there? Have you seen linear program for set cover? Primal dual set cover? No? Okay, does not matter. I think you have, I told you have seen, but let's say I allow you to, what does it say? It says that you can pick a set to a fraction. Okay, so earlier in set cover you're going to pick a set or you're not going to pick a set. But let's say you can pick a set to a fraction. So 0.1, 0.3, 0.5, 0.7. But, right, so you can pick a set to a fraction. Right, so a set can be selected fractionally. Okay. What does it mean to be a set cover then? So if it's picking each set S to a fraction, let's say f of S. F of S is the fraction to which we fix a set S. Okay, so some set can be 0.2, 0.3 and so on. So then what does the set cover mean here now? What does it mean to say that this element is getting covered? So earlier it meant that there is some set which covers this element. What will it mean now? Yeah? So you add up all the fractions which cover an element, they should add up to at least 1. So that's what it means. So now I'm going to change my problem. I'm going to say that, look, you maintain fractional set cover. Okay, I'm going to allow you some relaxation. So need not pick a set to 0 or 1, you are allowed to pick fractions. Okay, so which means that as you're saying that for every element, if you add up all the fractions containing an element E, this should be at least 1. And this fraction can be between 0 and 1. Now, how do I say that? Remember in the previous one, we said that once you pick a set, it stays with you. What would be the analog requirement here?
Fraction of the increases.
Good. So fractions cannot be decreasing. Fractions can only increase. Okay, over time these fractions will not decrease. Because that's like saying that whatever decisions you have made, you cannot undo those. Okay, so these fractions can never decrease. Why does it help? For example, in the example that I was trying to build for you, the bad example. Let's say there are many sets containing this element and you don't know which one to pick. So what will I do? I'll pick all of them fractionally. Then we'll amount all of them. So I'll hedge my bets across all of them. Okay? Something which I could not have done if I had to just pick one. But now I can spread my fractions all over them. Okay? So that's what I will do. Right? So far so good. And what is my cost? So earlier I was minimizing the number of sets. What will I minimize now? The total fractional value. Right? So yeah, so minimize, I want to minimize over all sets S, F of S. So this is exactly the set cover linear program if you have seen it. f of s are the variables. So you minimize sum over s f of s, and this is the
Sir,
constraint.
could you,
But it does not matter.
What it means to select a set fractionally, or just
Sorry?
what does it mean to select a set fractionally? Just the LP relaxation.
It's just an abstraction, right? So this is just a convenient way for me to say that because choosing integrally is too difficult. Yeah, so physically it means nothing, right? So eventually I still have to give an algorithm for the integral version,
Right.
but my algorithm will now be in 2 steps. Just like linear programming for approximation algorithms. What does it mean to have fractions there? Why did I do all that? Because it allowed me to at least get handle on the optimum, and then that's not what I'm going to output. I'm going to round it somehow.
Right.
So here also eventually I'll have to round this.
Right.
Okay, so but that step will come later. So in linear program we assume that you can solve a linear program optimally, right? Because there are algorithms for solving it.
If we
But here I can't solve it optimally because these constraints are coming one by one. Right? So it's like I have a linear program, but I don't know what all the constraints are. They're arriving one by one.
it's like an online linear program.
Online linear program. So there are papers which do exactly online linear program. And I could have done that, but that would be more complicated. I'm just going to show you a simpler version of it. Okay, but even that one will use very similar ideas. Okay. Okay. So in the remaining 10-15 minutes, let me show you how to do this. Okay. And the idea is again to spread it out evenly. So let me use some notation. Let M denote the number of sets. So what is it that I'm going to show you? I'm going to show you that I can build a fractional solution whose completed ratio will be order log m times the optimum. Okay, so I lose a factor log m here. And then as you're pointing out that this is not what I want to do, I still have to do a rounding. So when you do a rounding, you will lose another log factor. Okay, so when I do a rounding, I will lose another factor. What are m and n? M is the number of sets, n is the number of elements. But my algorithm will be randomized. So far I have not shown you where randomization is. You will see it is randomized. And then there are papers which are saying that this is more or less the best you can do. So you have to incur 2 logs. So that's the high level idea. Let me show you the algorithm. So the algorithm is the following. So you will initially give everybody very small values. So f of s is equal to 1 by m for all sets. Every set receives 1 by m. That's okay because what is the total sum here? This total sum will be 1. So you're incurring 1 initially, anybody will incur 1. So let's give everybody very tiny values. Okay? Now, an element arrives. Okay, so an element arrives and you check whether it is covered or not. So you look at all the sets containing it, you add up their fractions. If they add up to 1, great, you are done. If it is not 1, it is less than 1, what do you think I should do?
Increase fractions.
Increase fraction of the guys which contain it. How much? Well, I can't, 1 is too big, right? 1 means you are picking it completely. 1 is too drastic. By how much do you think actually increase?
1 by number of
1 by n, so maybe very slowly. Turns out that the right approach is to what is called multiplicative update. So whatever elements, whatever sets contain this element, you double everyone. Keep doing this. Okay, so while, so let's say element E arrives. Okay, so some element has arrived, and what I'm saying is that do the following. While you look at all the sets containing this element E, add up their fractions. So while this is less than 1. If it achieves 1, then you can stop your fractionally covering it. You double all of those guys. So f of s is equal to twice of f of s for all sets containing E. That's it. That's the answer. Okay. So everybody starts with 1 by m, then gets doubled at some point. So this is very aggressive, right? You're doubling everybody, but you will see why it's useful. The analysis is just 2 lines. So everybody happy with this? Okay, so now the claim is that when the algorithm ends, sum of fs is at most let's see why. So what is opt is the optimum set cover solution. Right, so this is the optimum set cover solution. So what I'll do is, remember when you double everybody, how much does your total cost increase? Well, all these guys were adding up to at most 1, and you doubled everybody. So what's the increase? At most 1. Right? Why? Because the increase is exactly equal to this quantity itself. So each time you do this step, you incur at most 1 extra. So you have to bound how many times I do that step. Right? So you incur exactly 1, at most 1. So you have to bound how many times you run that step while loop.
When 2 per k by m is less than 1.
Sorry?
Only whenever that summation of fs is 1 less than
If it was 1, if it was let's say 1/4, I only incur 1/4. So 1 is the upper bound.
As you're starting with 1 by m and you're
It will
doubling
be very
the
small
table,
initially, right?
so your 2 power k by m should be less.
Sure. But it's the utmost one. Right? So if I prove that the number of steps I do here is at most this much, then I'm okay. Right? Okay. So now how do I argue that I don't go there too often? And so here is my argument. So each time I run this step, okay, let's call this star. Okay, so each time I run star, we execute star. Well, what does it mean that you execute star? That there is some element et and you're trying to cover it. Now the optimal solution would have a set containing et, right? Because it's a set cover. I will say that I'm going to charge that set in that set cover. Okay, so we charge. Okay, so we charge the set in the optimal solution, or any set in the optimal solution, covering et. Okay, so far so good. So I say that, oh, this is the guy in the optimum, I'm going to ask it to pick. Right? Now, how many times will you ask somebody to pay? That's a question. So I am a set in the optimal solution, and how many times do you think I'll be asked to pay?
The number of elements that come.
Well, each time, remember, when this happens, that set in the optimal solution is also here. So each time you charge a set in the optimal solution, its fractional solution also doubles. And if you write 1 by m and you're doubling me, and if I hit 1, then of course this condition will never hold. How many times will I get doubled? At most log n times. So every set in the optimal solution is only going to get charged at most log n times. And then opt sets, so the number of times you will do this is opt log n. That's the complete solution. Okay, so every set in the optimal solution gets charged at most log n times. And the reason is that each time you charge it, its own fs value doubles. But how many times can you double its fs value? When you're starting at 1 by m, you have to go till 1, you only double it log n times. So that's it. So that maintains a fractional solution. Now the part that I didn't cover is how do you do rounding. And the way you do rounding is what is called threshold rounding. I will not analyze this for you, but what you do is you pick a number 0, 1. You pick a number alpha in the range 0 to 1. A random number alpha into 0 to 1. And then what happens is that any time somebody crosses alpha, you choose it. Okay. So anytime your fractional value crosses alpha, you select it. Okay. So that's essentially the rounding algorithm, and you can use some more analysis to prove that that works. But what I wanted to bring to your notice was that because the integral is very difficult, what we are doing is we are trying to maintain a fractional solution. And fractional solution allows you to hedge your bets, to distribute your sort of uncertainties across all possible solutions. So this is an idea which is used very often in many algorithms. So many graph algorithms, many scheduling algorithms. So you'll see that many of them will use this kind of ideas. So if you read a paper in online algorithms, it's very likely that they're using something like this. Okay.
Where did the randomization come?
Randomization comes at the very end, right? So if you are given these fractional values, but I want to get integral solution. So this is what I'm saying, you will pick a number alpha randomly between 0 to 1. And any time some fraction crosses that threshold, you'll say that. Okay. Stop here if you have any questions.
Can you explain what you said by incurring at most 1 at that distance?
Oh, see, you are minimizing this quantity here, right? Now, I have to eventually give a value bound on this quantity. Where is this value increasing in this step? How much is it increasing? So, well, this condition holds, and you are doubling each of them. So suppose this was 0.6, right? Some numbers are adding up to 0.6, and you're doubling all those numbers. What is the increase? 0.6, because earlier they were adding up to 0.6, now we're adding up to 1.2, so increase is 0.6. So the increase is whatever the current value is, which is at most 1. So each time you run this while loop, this number goes up by 1, at most 1. Okay? All right.
Let's try and Professor. Coffee break and we'll meet again at another.
Okay, let's start the second session for today. So the second session would be given by Ramesh Paul. He's a PhD student here at IISc. His main interests lie in studying something called planted models, which mimic real-world instances of hard problems. He generally likes to solve them using techniques like SDP and spectral methods. And today he is going to talk about SDP-based algorithm.
So welcome back to the session. Thank you to the organizers for inviting me for this talk. So I'm going to talk about Gomez-Williamson algorithm for max cut problem. These are the standard reference for this is the book by Williamson and Schmoes, but I'm going to closely follow the presentation given by lectures given by Ryan O'Donnell in the COVID time. So this is spring 2020. The videos of these are available online. I encourage you to check those out. Right, so we did see the max cut problem earlier in Prajakta's lecture. We're given an undirected graph, something like this, and the goal is to find a set S, a subset of set that maximizes the edges crossing the set. I'll call those edges as cut edges. These are edges going from S to the complement of S in the graph. This will be the notation for this. Okay, yeah, this will be the notation for this, yeah. So for example, here you can see if I have this set of vertices, if I look at this cut, you can see the edges that are actually being cut by this dotted figure. So this has a cut value of 3 because 3 edges are crossing the cut. So do you want to see whether this is the best thing we can do with this graph, this particular instance? Or can we do better than 3? So the problem, everybody recalls the problem, right? The statement is clear to everyone. Okay. We could join V1 and V3 as V2 and V3 as one thing, but then we lose the edges we are cutting between V1, V3 and V2, V3, right? So actually we can get 4. The idea is to club V5 to the side of V1, V2 and remove V4 from there, and this gives 4 edges in this particular instance. And in this case this is optimal, but more generally we want to do it, we want to find the maximum possible cut, not by inspection because, and we did see like Professor Prajakta talked about I think the greedy cut based algorithm and also the random cut algorithm where we just take a random cut in the graph. And we may also see a local search algorithm later in the school. But all of these, these give 0.5 approximation for this problem, right? And this was an open problem for a really long time. For example, this random cut algorithm, I suppose people knew this before, but very formally you can find it in a paper by Idosh in 1967. And this problem was really open for decades. Okay, so before that, one exercise is to find tight examples where these algorithms that we discussed earlier, they give 0.5 approximation ratio. Was this a tutorial question? Or the question whether we can find a tight example for, let us say, the greedy cut algorithm. Okay, then I encourage you to solve this exercise where this algorithm gives half approximation. The analysis is tight. That is what I mean by tight example. And there was really no progress on this problem for like decades. And you may ask what people were really trying to do with this problem, but like, and one thing that we've seen in the school so far is that linear programming help us make progress on such problems, right? And we've seen a lot of linear programming based algorithms, so let us see. So in fact, this is what people are trying. People are trying a lot of LP approaches to solve this problem. So, okay, I think I gave away the decision variables, but that is not too hard to guess. XV are just indicators of whether a vertex is in the set or not in the set. So recall I had this set S I wanted to find, like that also, if I find the set S, that also defines the cut edges in the graph, right? So what should be my objective function? Maybe that would be a good thing for you to guess.
Summation of edge weights times.
So for now I'll just take unweighted graphs. Everything in this Everything I'll discuss will work for weighted graphs as well. Okay, but for now I'll take unweighted graphs. Yeah, so summation over edge weights are 1. What is the objective function there?
So if you consider like all edge weights to be 1, then like summation of xv's you want to maximize summation of xv.
Maximize summation over?
Because
xu. Oh, no, like we want the edge to be cut, right? Somehow that has to come into the picture as well, right? It is not just it's not just a function of a single vertex, right? The number of edges cut is a function of 2 vertices that participates in the cut, right?
I was thinking you take one edge and that you
so maybe
make it
you
0 when it's not cut.
Yeah, so maybe you have a different LP where you have a variable for an edge. Okay, but for now let's stick with this LP where we have a variable for a vertex. And yeah. XU plus XV.
For every age,
right.
XU plus XP mod 2 something kind of.
Okay. But if it XU and XV are on the
XU plus XV.
plus XV, but if they are opposite side of the cut, we should get 1, but we are getting half here, right? If we do mode 2. Sorry, mode 2 you mean, okay, you get 1 here and, but okay, yeah, so we can do that. And well, that is not a linear constraint, right? The mod function is not a linear constraint. Maybe somebody has another suggestion?
So for any edge, any cut edge, one of the vertices will have a value of 0 and others should have 1.
Exactly.
So the difference should be 1.
Yeah, so
we can maximize the differences.
Yeah, but we need to also, like 0 minus 1 should also be counted as 1. So actually what you are saying is right, we need this indicator function. This indicator function is when x2 and xv don't have the same label, it gives 1. Like it takes, the function takes 2 variables, x2 and xv. If it is not, if they are not same, then it gives 1, otherwise it gives 0. And this exactly captures the max cut problem. Like well, the problem with that, as it was with the other suggestion, mode 2, is that this is a highly nonlinear constraint, right? Okay. Sorry?
Is the indicator function linear?
No, the indicator function is highly nonlinear, right? It's like a delta function kind of a thing, right? It, yeah. In fact, it's a nonlinear function, yeah. Okay, so now one equivalent way to capture this and see why this is a nonlinear function is that this is exactly equal to this function on the top. Maximize this function, right? The indicator function is exactly equal to this when xu are 0 and 1 variables, right? Sorry?
I think a lot of.
Okay, good. Yeah, it may be missing in a lot of places then. I'm sorry, I made this slide last night. Okay, yeah. So, okay, one, like of course you can try to, for example, I think in the tutorial you saw one way to write an LP for this. We'll come to that, okay. But one, like a very methodological way to write a relaxation for when you see these kind of absolute value constraints, because these are like linear constraints, almost linear constraints, right? But still they are non-linear. So one, like a very methodological way to do this is, let us say we have a constraint of this type, absolute value of x less than or equals to t, x is the decision variable of an LP, is to introduce an auxiliary variable y, which stands for absolute value of x, okay? And then you add these two constraints, y is greater than or equals to x, y greater than or equals to minus x, okay? And we capture that y was supposed to stand for absolute value of x, and then the constraint that absolute value of x is less than or equals to t, you add y less than or equals to t as a constraint, okay? So if you look at the picture, you really have a one-dimensional picture, and in some sense you lifted your polytope to a higher dimension, something like this. Okay, the original constraint was you only had x values, there was no y, x will belong to minus t and plus t. Okay, now you added these two lines, y greater than or equals to x, y greater than or equals to minus x, and y less than or equals to t. And the idea here is that if you project it back to the original dimension, what do you get? You get the same thing. Absolute value of x less than or equals to t. If you project it back to the x dimensional space, the original space, so this is something called as extended formulation, extended LP formulations. There is a very rich theory of these. So in some sense, these, the absolute value of constraints can be very well handled by adding these auxiliary variables. So let us see. Let's try to do this for this particular LP relaxation we wrote. So firstly, is this clear? Does anyone have a doubt with this? Okay, let's move then. Let's try to do this for our particular LP with a summation there, of course. Yeah, okay, maybe, yeah. We will just do that, do exactly what, again, summation is missing here. right? So we have this. So we don't even have a constraint of the form absolute value of x less than equals to t here. We just want some yuv to stand for absolute value of xu minus xv. What does that mean? That just means add these two constraints over here. Okay, and I add these two constraints over here, right? And I do the natural relaxation, which we have been doing so far, which is xu is a number between 0 and 1, right? That is a natural relaxation. So what do you think? Is this a good LP relaxation for this problem? Or do you see any issues with this? I hope the LP relaxation is clear, right? The LP is in the variable yuv. They were supposed to stand for absolute value of xu minus xv. So they are like the indicator variables. One if an edge is cut, but what he was suggesting earlier, right? We add these constraints to capture this absolute value constraint. We add these two constraints, right? These two constraints, right? So is this LP fine, or do you see any issues with this LP? Notice, yeah. Yeah. Sure. Yeah. You can add that constraint as well if you want to. But there is something more wrong with this LP. Does anyone see this? Just look at yuv variables, right? Like what would you, if you are in the shoes of an LP solver, what would you do with yuv's if you are trying, somebody is asking you to maximize yuv's, summation over yuv's? Yeah, you'll just set it to a very large value, like, right? So you can get infinite objective value with this, right? So this LP is useless. Okay. Notice that this trick of handling absolute value constraint does work for the minimization version of this, like the minimization version of this problem, which is the min cut problem, or really the min-st cut problem. Okay. You just need to add this extra constraint that x is 0, xt is 1, right? And this LP will actually work for the min-st cut problem. And the fundamental reason here is that you're trying to, in min-st cut, you're trying to minimize this absolute value constraint. So it's like a convex function. You can minimize convex functions. So fundamentally, that is what is going on here. So this LP doesn't work. It gives infinite objective value, but we can try to do pattern matching here. Okay, we can still try to, we know this works for minimization. Maybe let's just try to add the opposite side constraints for the maximization version of the problem. That makes sense. Okay, is this LP any better? See the LP? I just like switched the, yeah. Exactly. Yeah, so these force v to be less than equals to minus 1, which is not what we want, right? Uv are intended to be 1 if an edge is not cut. So again, this will be, this is a useless LP.
I would guess it would force it to 0, like set everything to 0 and then...
Yeah, but then it doesn't really capture the cut.
It doesn't do that, but I guess it would...
Yeah, we can add more constraints, and in fact, that is what I want to come to. It's not that all LPs are useless. We're trying to do it in a very special way using this absolute value constraints. But you can try to anyways do things what you can. For example, this is an LP I believe all of you saw in the tutorial session, because I've lifted it from your tutorial session. So, so I believe you saw a half approximation for this LP, right? Well, now I'll show you like that this LP can't really do better than half. Okay, and how do we show that? Using integrality gap construction, right? So let us see. So what values do I want to set you? So the only changes I'm using yuv, while this is using euvs. That is the only like the notation change here. Otherwise everything is the same. Okay. And what does this? How large can you make this LP value? Well, I should talk about a graph, but okay, I mean, I don't even want to talk about a graph. I can even, for any graph, I can make this LP value quite large. Number of edges, exactly. How do we do that? What is the variable? Yeah, so everybody can think about that. Meanwhile, how can we get number of edges? Yeah. Okay, so the way we do it is, we set xu equals to half for every vertex, and euv equals to 1 for every edge. Okay. notice that all the constraints are satisfied. I'll give you a moment to check those. Right? And so LP opt is E. Okay. Now to show an integrality gap, I have to show a graph where the opt is, let us say, E by 2, or close to E by close to cardinality of E by 2. Do you know of any such graph where the max cut value is close to half? A way to think about it is, where would a random cut algorithm fail very badly? Like, yeah.
Take a bipartite graph with.
The bipartite graph will have everything as a, the max cut value is absolute value of E. It's exactly M. So want to go, yeah. Want to do something else. A cycle graph. So cycle graph is, sorry. Yeah, but like, okay, that is true, but we can't quantify an arbitrary strongly connected graph. It is the strongest possible connected graph. This is a clique. Okay. In a clique, the whatever you can work out this calculation, whatever the number of edges you try to cut is, others as in number of edges by 2. The best way is just divide, like take any n by 2 vertices, n by 2 vertices, define the cut there. Roughly E by 2 because E may not be an even number, cardinality of E may not be an even number. Okay, so this shows an integrality gap is half. So this LP, although is better than previous LPs, at least it captures the problem in some sense, and it also gives a half approximation, but is also stuck at half. So in fact, we can ramble on and talk about various more LPs, but we'll not do that. And the reason we'll not do that is this is in fact known for this problem. Okay, that there is no there is no polynomial size LP, for example, which can beat this half approximation. Okay, so we truly do need something else. LPs are at least polynomial sized LPs. Notice that I'm saying polynomial sized LPs. You can't beat. Let us go on, move forward. So this brings me to what we are going to talk about today. We're going to talk about a state-of-the-art 0.878 approximation algorithm for this problem. Okay, a big improvement over 0.5. This will be based upon I can give you various buzzwords: convex programming, semi-definite programming, huge LPs, separation oracle, blah blah blah. But all I want to convince you today is that SDPs are just LPs with an extra power, one extra power. Okay. And we'll try to, hopefully by the end of the talk I would have you convinced and made this fact more formal. Okay, so for some reason which will become clear much later in the talk, I just want to do a notation switch. Okay, instead of talking about 1 0, which is I believe what we have been doing in the school so far, I want to talk about +1 -1 kind of indicator variables. Okay, so this is the same thing. If u is in the set, I put xu equals to 1, otherwise I put -1. Okay, and this is and to really convince yourself that this is for convenience, it will be a tutorial exercise to do whatever we do today using 0 1 indicator under variables. Okay, so this will be a tutorial question that you will try to solve, and that will convince you that this is really a notation switch and nothing more than that. Okay, so now how do we capture? So as the title of the slide says, no linear constraints, right? So maybe now the linear programming we saw, like limitations of linear programming, like no polynomial size LPs can capture this, get a better than half approximation. We have a lower bound. So like what kind of non-linear constraints do we want to allow? Do we want to allow any non-linear functions, exponential, trigonometric functions? Well, for now we'll stick ourselves with the most basic class of non-linear functions, which are polynomial functions. And even with polynomial functions, we're going to stick with, let us say, quadratic functions. Okay. So let us see. Now with this quadratic function, can you capture this LP again? The variables are -1 +1. Can we capture the objective function using a quadratic function? Sorry? Summation xu xv, but xv are now -1 +1. Right. Right, but that will not actually, that will be related to the number of cut edges, but it will not exactly be the number of cut edges. What we will do is we will take a minus, let me show it to you. So again, we want to capture this indicator function, and this is what we will do. Okay, recall that xu being +1 and -1, we can just write that as xu square being equals to 1, right? xu square equals to 1. And what you were trying to say, minimize xu, xv, we are going to do something related, we are going to maximize minus of that plus with a factor half added to it. Why? Because now if you look at some true solution where like xu is plus 1 for some cut and minus 1 for some cut, then it exactly captures the number of edges. I'll give you a moment to convince yourself about this fact, right? Because if xu, xv are on the opposite side, it gives minus 1, you get 1 for that term, and if they are on the same side, you cancel out 1 and you get 0, right? Your question?
We just didn't expect the sums to be missing everywhere.
Oh! I see that, yeah. So, okay, what this shows is that the quadratic program, of course, this exactly captures the max cut problem, right? There is no relaxation, anything, this is exactly the max cut problem. But what it will do is, it will try to, for example, if we try to solve this problem, it will try all possible plus minus 1 values for xu, and for every possible plus minus 1, it will actually get that particular cut, if we have that summation, and then it will output the maximum of those cuts. Okay, so this is exactly the max cut problem. So max cut is, this shows that quadratic programming captures max cut, so quadratic programming should be NP hard. In fact, not only that, it also captures something we studied earlier and which was clearly more powerful than LPs, which was ILPs, right? So Professor Neil Dhara Mishra talked about ILPs where we have xu being 0 or 1, okay, or xu being plus 1 or minus 1, and quadratic programming can even capture ILPs. For example, does anyone see this? For example, if I have a constraint that xu is 0 or 1, how does quadratic programming capture that?
xu square equal to x captures like 0, 1.
Yeah, xu square equals to xu. Yeah, exactly. Yeah. So that captures ILPs as well, right? And of course, here we have 1 minus 1 that can be captured by xu square equals to 1. So QP is at least as hard as ILPs. Okay. Okay. So right. So, but where are we going ahead with this? So I promise you that SDPs. Okay, we are not even at SDPs yet. Okay, but it seems we have moved far away from the linear land now, right? We have quadratic functions and all. So I'll do one thing. I'll do some change of variables. Okay. This is literally doing nothing. I'm just rewriting something like this is a quadratic program. This is a very quadratic program. I want to at least write it as, I want to get some linearity out of this. Okay. And here is one trick I'll use. I mean, it is just a change of variables. Okay. But it will be helpful. Let us see. Okay. So let us say there is, let us say that for every xu xv we add this variable yuv. Okay. So yuv is supposed to stand for xu xv. So now we can actually, now we can actually use that to write this LP or quadratic program really, not LP. How? The objective function becomes this thing, right? And we have this constraint xu square equals to 1, that becomes yuu equals to 1, right? And we also have yvv equals to 1, or more generally we have yuv equals to yvu. Let us add that explicitly, even though it is clear from this constraint. And of course we have to add this, right? To have this program equivalent to this program, we have to add that what is our meaning of yuv. They are supposed to stand for xu xv. Okay. Is this equivalent formulation clear, or are there any doubts with this? I'm just like written. So why I've done this is because now we can see that this is the only problematic constraint. This is still a quadratic program. I'm not saying this is not a quadratic program, okay? But this is a highly quadratic program. Somewhat you can see some linearity appearing here, okay? But of course we have this problematic constraint yuv equals to xu xv, so still this is an equivalent quadratic program. Okay, let's proceed then. Right, so the key idea today is going to be that we are going to model such problematic constraints using linear constraints. Okay, so this is the problematic constraint yuv equals to xu xv. We will try to model this using some linear constraint, and we'll make this precise in a while. How do we do that? Okay, let's see. So do you have any suggestions for, maybe this is not the right time to take suggestions. I'll maybe directly tell you. Okay, yeah. So maybe the first idea could be, this is like really the source of all trouble. So why don't I just drop this constraint? like we do with like our life. When we have a problem, we just try to ignore it. Let's try to do that here. Right. So okay. So one another thing I want to do is these variables y u v's. Okay, these are just n square. Some like they are defined for every pair u v. Right. They are just n square numbers, but I just want to put them in a matrix. There is no matrix structure per se. Okay. It's just I want to put them in a matrix for my convenience. Okay. So these should be n square numbers. Okay. I just have written them in a matrix instead of a long vector. Okay. Yeah. So now the idea was that we'll try to ignore this problematic constraint, and just if we ignore this, then this is really an LP, truly an LP, right? If I just ignore this constraint, this was the only quadratic constraint, it really is an LP, and we can try to solve that LP. Okay. So do you see what the problem with that is?
Why didn't we put any constraints on x, u and x?
Right. Yeah. So the constraint that xu square equals to 1 is captured by this. So like yeah. So everything yu indeed capture the original constraints on xu. For example, we had this constraint, right? Xu square equals to 1. It's the pointer. Oh, sorry.
I mean, anything that is like y u v u not equal to v can be very small.
Sorry.
Any like you do not have a bound on y u v where u is not equal to v.
Yes.
So it can be very small.
Yeah. That is a problem with this LP, but I want to first address the question here. Like, is this clear? Why I'm saying we can? Yeah, because xu square equals to 1 is really if we agree on this constraint, then xu square is yu. So when we are saying yu is 1, this is really capturing xu square equals to 1. Okay. And I can explicitly add constraints on xu, but really the way I want to do is I really want to have this non-linear constraint, everything else to be linear, and I want to model this as a linear constraint. Let's see. So as I said, as you pointed out, like but the problem now is that if you ignore this constraint, okay, then really you are just asking for any arbitrary numbers. So the LP is going to lie. For example, it may say what was your constraint? You wanted yu to be 1. I'll just put yu as 1 on for every entry, right? For every vertex, and I'll just put minus infinity everywhere else, and this gives you infinite objective value, right? Okay. So correct, yeah. Does everyone see this? Like we really shouldn't expect, because this was a truly quadratic program and we just tried to ignore a constraint, like the source of all our troubles, we just try to ignore it. Doesn't often work in real life as well, so we shouldn't expect it to work here as well. But okay, so the idea was that we were trying to model this using some linear constraint, but looking at this construction, can you already see like there is some trouble by this, like we should already be able to say something about yuv's, like can we add a constraint, or basically I'm trying to ask, can we add a constraint on yuv's which is implied by this constraint, the constraint that we just tried to ignore, the problematic constraint.
yuv greater than -1.
Exactly, yuv greater than equals to -1. Okay, so if xu xv were indeed +1 -1 solutions, yuv would always be greater than -1. Okay, but that is not a justification to add it. That is what we hope to add. Okay, let us be clear on that. We'll see why we can add this constraint in a second. That is just our hope, that we intended xu xv's to be +1 -1. Okay, indeed it is true for the quadratic program, but then we try to ignore the quadratic program, the quadratic constraint. Then we try to only look at the linear constraint, right? So then it's no longer true that xu actually captures. There is always a x such that yuv equals to xu xv. That is not clear at all, right? We just ignored that in RLP, right? So we would really want to add this particular constraint instead of adding all these constraints. We just really want to add this constraint, yuv greater than equals to -1. Okay. Well, why is this constraint helpful?
Because it's at least bounded by negative.
Yeah, at least this minus infinity problem goes away. So we'll see this. We'll see this in a second. But first, I want to convince you that why can't we really add this constraint? Well, yuv were supposed to be yvu, so we should really be adding yuv plus yvu greater than equals to -2, right? Recall that there are some yuv is supposed to be coming from some xu xv, okay, and the -2 I can write as yuu plus y. Yeah.
So why is that different from?
Sorry.
Why is the second line different from the first line? Exactly.
How does the second line follow from the first line?
No. How is it different?
It is the same. It is the same. I'm just saying that I just write 2 as yuu plus yuv. Is this clear? I'm just saying write 2 as yuu plus yuv. Just. Yeah. But notice, if there were YUVs that were XU, XV, what would this have been? Does anyone see this? If YUUs were indeed, there was some XU, XV where YUV was XU, XV, what would this have been? This would be XU square
plus XU, XV plus XV square.
Sorry?
XU plus XV the whole square.
Exactly, yeah. This is just XU plus XV the whole square. Now, that is why I can add this constraint, because this is true in any world, right? XU plus XV square is greater than or equal to 0, right? So actually you should argue in the other direction, okay? This is our motivation, but really this is always true, okay? Now if there exists some YUV, if there is a world where YUV is equals to XU, XV is a constraint that does hold, in that world we can always open this up, replace it by Y variables, use the constraint that YUU, YVV is 1, get this constraint from where we can get this constraint. Okay, so the reason we can add is this, because this holds, because this is an inequality that always holds. Okay, so this is a constraint that is derivable from the, so this is a constraint we'll add to our LP now. Okay, earlier we had ignored everything, now we just added this one, like this constraint for every edge. Okay, so recall that this now becomes an invalid solution, right, because we have this constraint. So as somebody was pointing out, now we can, okay, the summations finally do appear. I hope they do remain with us. So now we can only get absolute value of E. Okay. At least now this looks more sane, right? I mean, should not be able to cut infinite edges. Should only be able to cut how many edges there are in the graph. So okay. So at least yeah, passes some basic sanity checks. Let's see. What else can we say? Okay, but we really want to like yeah. So we can also show that LP opt is so this shows that LP opt is less than or equals to E current E. Okay, but now let us look at this graph, right? This one. Yeah, let us look at this graph, a triangle graph. Okay, there are only 3 vertices in this graph. Okay. Well, with the previous constraint, like this is a valid solution even now, right? So you can indeed get, like LP opt can be made indeed 3, right? But yeah, but yeah, there's a max. Yeah, it should be, yeah.
What was the question?
The question was whether this inequality seems to be in the wrong direction, because we have a construction which gives absolute value E, so we are maximizing, so the LP opt should be indeed greater than or equals to E. Yeah, that is correct. Yeah.
Minimizing the negative of Y.
Minimizing the negative of YUV, yes. So that is why we get YUV are -1.
So the inequality is correct, right?
No, so we give one construction of this matrix YUVs. This matrix already achieves absolute value E, okay, and we are trying to maximize this objective function, right? So there is one construction of this matrix which achieves. It seems confused.
The point is that LP opt is the thing with the negative sign, so it is.
Are we minimizing the objective or are we maximizing the objective?
We are maximizing the objective. We are minimizing, like yeah, we've written in terms of IU, like yeah, but this is the whole objective, and we are maximizing this. Okay, so right, so we can get -3 with this, right? LP opt can be as large as 3. Sorry, LP opt can be as large as 3, right? But do you see issue with that? Like in this graph, can max cut be 3? How large can max cut be in this graph? It can be only 2, right? So clearly opt is 2, but LP opt is like still sort of trying to do like much better than that, which should not be possible. So it's clearly missing something. So let's see, what do you think based upon what we did? Like earlier we added this constraint. So yeah. So now how does it get 3? It gets 3 by exactly this kind of a matrix, right? That gets you 3. But exactly setting these sort of variables, right? It gets 3. So what do you think we should do about this now, so that it doesn't get 3, it gets 2 in this particular graph only? let me. Right. Yeah. So maybe you mean to say that out of these three, like this, like all three cannot be -1 together, right? So maybe you want to say yuv plus yvw plus yuw is greater than -2, right? Yeah. Or I will add something even more stronger. I'll say -3/2. Okay. And again, why should we even be able to add this constraint? It's going to be very similar. Okay. Firstly, let us again see this constraint is helpful. If you actually plug in these values, LP opt was earlier giving you 3. You can see that LP opt is now 9/4. Okay. Again, ignore the less than equals to constraint. Right. Okay. Again, why the reason we can add this constraint again, and this is something you should check, is that really this is something. It follows from this constraint. If you just open out this square, okay, you will actually get this constraint. Okay. So notice what we have done. So notice that this is already giving us some sort of an improvement, right? I mean, opt is yeah. So yeah, I believe all the inequalities are in the wrong direction now.
That will check
Yeah.
if they are awake or not. It's fine.
Yeah. Right. So okay. So like this gives you better than. So earlier notice that opt by LP opt ratio was 2/3, right? So this is giving you a 0.67 approximation ratio. Now we have shown that LP opt is yeah. So So we know that opt is 9/4. So L divided by opt is 8/9. So it is 0.889. So this ratio actually does improve by adding this. In this particular graph only, this ratio does indeed improve. So notice what is the general pattern of things we have been doing so far. You have already started to see things that we always try to add an obviously true constraint, okay, which is the following constraint, which is the following form. Okay, we just take some x1 plus x2, some number squared that is always greater than equals to 0. We just open it up and we just use that xuv was equals to yuv was equals to xu times xv, and write as a linear constant in the yuv variables. That is the general pattern of how we have been deriving these constraints, right? And we really hope that these constraints do a good job of capturing yuv equals to xu xv, because that was a highly nonlinear constraint, a quadratic constraint. We couldn't write it up, and we just added these proxy constraints for that. Okay. Notice that all the constraints that we derive are finally in the yuv variables, right? And they are exactly derived using this, and the fact that sum of squares is always a non-negative thing. Okay, the basic fact. And this is what is the SDP constraint in the SCP. Okay, related to this. So firstly, how many such constraints are there? So maybe if you look at this constraint, right, we add for. If you focus here, like, yeah, we can add any multipliers with x1, x2, right? So for example, here the multiplier was 1, 1, 1, right? But we can have 2 times xu plus 3 times xp minus 7 times xw square greater than equal to 0, because square is anyways greater than equal to 0, right? So we can have any coefficients multiplying with xu, xv, xw, and so on, right? So really this can be any arbitrary numbers, right? So how many constraints are there in this LP now? Infinitely many, right? So what do we do about this? So we know that LP solvers can solve LPs, but this is having infinitely many constraints. We'll get to that. We'll address that question soon. But before that, this is what I said. This is the SDP relaxation. I'll write it out very explicitly. This is originally due to Dalrom and Poliak. Government and Williamson actually analyzed this SDP. The formulation is due to these guys, and explicitly this is the SDP. Okay, right? Maybe this doesn't make sense right now. Let's ignore this. Okay, basically you just write the infinitely sized LP. That is the SDP. So now let us see. Actually, explicitly see what are the constraints. I said we only get linear constraints, right? And you get infinitely many of them. Let's actually see it through a short calculation. So whenever we get something like this, summation over cu xu square, we can just open it up. open up the square. Okay, and we know that there is a world where we are trying to derive constraints from YUV from XU variables where XU XV equals to some YUV, right? We are only deriving constraints from that original constraint, the quadratic constraint that was always there, right? We are only deriving constraints from that. So let us put that, use that here, okay? And now can you see some, so of course these are linear constraints, CUs are some numbers, right? So these are linear constraints in YUV variables. Can you see the pattern emerging now? Like what should we, if, okay, maybe let me help you a bit. I'll just rewrite the summation. Do you see the pattern now? What is this term? Recall that I asked you to think of Y as a matrix. At that time I said it was just for simplicity, but yeah, this should help you now. What is, for example, what is this term?
C transpose.
Yeah, C transpose Y, or I can write it Y times C. Y times C actually, yeah. And this whole thing is C transpose Y times C. I hope you see this, right? Okay. So what were all these infinitely many constraints saying? They were just saying that C transpose YC is greater than or equal to 0 for all C, for all possible C. Like there are infinitely many possible C's, so still there are infinitely many possible constraints. Okay. I just written it in a clean notation using the matrix. Okay. This is actually equivalent to saying that a matrix Y is PSD. This is the definition of a matrix being PSD. There are various equivalent definitions. We'll look at a few of them. But yeah. Let's see. Okay, yeah. So we say a matrix is PSD. All of these are equivalent definitions. We'll see this soon. That these are equivalent definitions. Okay. The first definition says that all the eigenvalues of a matrix are non-negative. The second definition is exactly what we have here. And the third definition says that we can write the matrix as the product of two matrices, W transpose W. Okay, and actually we'll use all three of them today. Okay, but yeah, the point is these are infinitely, I said I'll get back to this, there are infinitely many constraints in this LP. So how do we solve such huge LPs which have infinitely many constraints, right? So this is where I like, sorry,
So we are still not sure whether that captures my quadratic constraint, though we are hopeful.
We are hopeful because we have really tried to like add in some systematic way. We have tried to add a lot of constraints, and
right, so will we end up proving that it captures?
It will not exactly capture because original quadratic programming is like captures max cut, but it will do better than what so far we were able to do with whatever linear programs we saw at the start of the lecture. So it is clearly having much more constraints than that, and those constraints will be able to do a better job. We can do a better job with those constraints.
Right.
It does not exactly capture the problem, if that was the question. Because clearly, there are many more constraints that are implied by YUV being equals to XU XV. We have only seen a few of them. We have seen a very a trivial kind of constraints that follow from this, like just by writing combination of X and saying that the square of them is greater than or equal to 0. We have only added those trivial kind of constraints. There are many more constraints, so it will not exactly capture the problem. So now the question is, how do we solve such huge LPs? Because we really have infinitely many constraints. So now this is I'm really struggling on time here, so I'll try to skip most of it. I'll just try to hand my way through this. Firstly, the first point is really trying to optimize an LP is equivalent to finding a feasible solution. Have most of you seen this? That finding a feasible solution to LP is no harder than solving an LP, although it may seem like optimizing is doing a much more job, but actually using strong duality you can just write this big LP which captures this idea. So optimization reduces to checking feasibility, and really the way we should think about handling infinite constraints is using this ellipsoid method, which Professor Neil Zara Mishra didn't talk about but briefly touched upon. It's a slow algorithm, but it is really good with this kind of stuff. Okay, I'll not go into the algorithm. Basically, intuitively, the algorithm tries to. So this is this orange thing. Where is the pointer? Okay, yeah. So this orange thing is the polytope. Okay, so we start with a huge ellipsoid. Okay, we were basically trying to capture this polytope, and based upon some if the center of the ellipsoid doesn't lie in the polytope, we'll try to cut the polytope and like reduce our search region, and eventually hoping that we finally get some point inside the polytope. Remember that I said we are only asking for feasibility now. Feasibility is equivalent to optimizing. I just want to say whether this is feasible or not, and you can show that this ellipsoid the volume shrinks fast, and you can show that basically there are a lot of things, there are a lot of questions here you may ask, but I am going to skip all of that. The only thing I want you to so the main thing I want you to notice about this method is that which I didn't show, the method I didn't show, but the only thing is it doesn't actually require an LP to solve it. Okay, the only thing this method requires is if this point, the center of the ellipsoid is not inside the polytope, you give me some hyperplane separating the polytope from this. Okay, so this should always be possible. The point is outside the polytope, right? So you actually don't need all the constraints. Okay, this method only asks you to find such an hyperplane. Okay, so in other words, if I am given some point and if that point doesn't satisfy the polytope, okay, if it does satisfy the polytope, then this thing should give me yes as answer. Okay, and if it doesn't satisfy, then it should give no as an answer. Plus also there should be some inequality that is unsatisfied. It should give me one such inequality. Okay, for example, here it can return this hyperplane. This inequality is unsatisfied, so it can return a hyperplane that separates it. Okay, so this is what is called a separation oracle. Okay, I didn't ask you to write out all the constraints even, right? If the ellipsoid method just the ellipsoid method runs and you are able to give such a separating hyperplane, it will run because that is the only thing that it wants from the polytope, right? The only thing it wants from the polytope is this hyperplane, right? And the main idea is that these separation oracles can be designed even for huge LPs with infinitely many constraints, because we don't even need to write the LP. Okay, whenever we try to solve the LP, we have to somehow start with you can imagine starting with a very big ball which captures your polytope. Okay, and then it should definitely if you start with large enough ball, it should capture the whole of polytope, and then you are just saying, okay, this should be feasible. You start this cutting the ellipsoid thing, and then you're only asking for a violated inequality. If we can do that, it's not clear we should be able to do that. If we can do that, then we can solve the LP even without writing out the LP, which we clearly can't do because we have infinitely many constraints this time, right? So to impress upon this idea, instead of directly going to the problem, I'll show you a demo sort of a thing where this idea works. So I suppose you would have seen the min-cut LP, right? But maybe not this formulation. How many of you have seen this formulation for min-cut LP? You've seen this? Okay. So really what we are saying is like there are, for example, this is a source vertex, this is a terminal vertex. There are like many possible paths between source and terminal. Okay. So if you really think of XC as 0, 1 variables, what this constraint is saying that for every such path, because all paths have to be cut, right? There is some XC that has to be 1 along this path, right? So that is what this constraint is saying, and we can relax it in the natural way we do it, right? But now we want to solve this LP. Okay. How many paths are there between some fixed S and T in a graph? Exponentially, right? So this is not a infinitely sized LP, but again this is an exponentially sized LP. So again you might think that okay, there are exponentially many constraints, I can't really solve this LP per se, right? But we just now learned that if we can find a separation oracle, that also works for the ellipsoid method. So what does a separation oracle mean here? It would mean that if this constraint is satisfied, I output yes, and if this constraint is not satisfied, let us focus on that case. Okay, if this constraint is not satisfied, then some inequality must be some inequality must be false here. I want to return such one such constraint. So how do we do that? If we can do that efficiently, we can actually solve this exponentially sized LP. So how do we do in this problem, the min cut problem?
Shortest path.
Sorry?
Shortest path.
Exactly. Does everyone see this? Maybe not. Yeah. So what we can do is think of XCs. So WEs are like what we call the weight or cost in the problem, right? I'm calling it weights here. Okay. And XC of course capture whether you're cutting that edge or not, right? So if X doesn't, so what we can do is XCs are non-negative numbers, right? So we can indeed think of XCs as edge lengths. Okay. So then what this constraint is saying is that for all possible paths between S and T, the distances should be at least 1. For all possible paths between S and T, the distance should be at least 1. Okay, but there are exponentially many paths. So what we can do is we can say, okay, instead of saying all possible paths, we can say the distance of the minimum path from S to T should be at least 1, right? That would imply this constraint, right? And indeed we can solve this. If we think of X as edge, you can just run the shortest path algorithm. Okay, that runs in polynomial time, and that is your separation oracle. So the shortest path distance will actually, that is your separation oracle that actually solves the problem. So we can, that is how we will solve this LP using ellipsoid method. Okay. Right. I know this part of the talk may be slightly sketchier. Maybe this example helps a bit, but even if it is, if it doesn't help, we'll not need it in the last part of the talk. Okay. So the point is, okay, maybe due to in interest of time, I'll skip proving that all these are equivalent formulations, though I will use it, and I have slides. Actually, these are just one-line proofs. Just require some linear algebra. I'll skip this. We can basically here I'm showing that all these are equivalent definitions of a matrix being PSD. You start with any definition and you can derive the other one. You can go in this cyclic fashion. You can follow these orange edges and you can see all of these are equivalent. Okay, I'll skip due to in interest of time I'll skip this proof. Okay, so now notice that we had these infinitely many constraints, right? So we had these infinitely many constraints which we said were equivalent to saying that C transpose YC is greater than or equals to 0, right? Those infinitely many constraints are equivalent to saying this, which is equivalent to saying that a matrix is PST, okay? Which is like still there are infinitely many constraints, but now can we design a separation? We know that separation oracle will work, right? So now can we design a separation oracle? What does that mean? Okay, like if we are given a PSD matrix, and it is indeed a PSD matrix, the separation oracle algorithm should output yes. Okay, and if it is not a PSD matrix, then by definition there should be some C such that it makes C transpose YC negative. We should return that C. If we can do that efficiently, then we don't need to actually write this LP. You can just output this C whenever the ellipsoid method asks us. We can just either output yes or we can just output no and give this C. And with a bit of effort, you can actually verify that we can actually find such C. And the reason we can do that is using this characterization of a PSD matrix, that it has all the eigenvalues non-negative. Okay, why? Because here is the separation oracle, the polynomial time separation oracle. Compute all the eigenvalues. Okay, if all the eigenvalues are non-negative, output yes. Okay, if that is the case, the matrix is truly PSD, right? If a truly PSD matrix is given to you, it will indeed have all the eigenvalues non-negative. Then this correctly outputs yes. What about if the matrix is not PSD? Okay. But you need to return a C, not an eigenvalue.
Eigenvector of the.
Yes, exactly. So there should be some eigenvalue which should be negative, right? And its corresponding eigenvector, we can return that as, and we can quickly verify through a small calculation, right? If we put that eigenvector instead of C, this eigenvalue is negative, right? So Vi is an eigenvalue of Y and its negative eigenvalue. So this lambda I is a negative number. And this lambda is a negative number, so this whole thing is negative. Make sense? Okay. Yeah. For a long time I thought this is actually the separation oracle. This is actually, there are some issues with this. Actually you need to do something else which is called a LDL transport. I'll not talk about that, but the key point is that in principle this works, but due to some numerical issues there are, like, this is not a polynomial time separation oracle. but the point is there's something close to that related to this which works, and it can actually solve the ellipsoid algorithm. We can use the ellipsoid algorithm to solve any SDP. What is an SDP? LP with this additional constraint that Y is a PSD matrix. Right? So we can actually solve this using the ellipsoid algorithm. So even though we had if you didn't follow through the last slide, it doesn't matter because we'll not need it for the final part of the talk. The point is that we can solve such huge sized LPs. Specifically, we can not always solve them, but for our case, when we have this special kind of a constraint which are only constructed by having squares, right? We constructed our constraints only in a specific fashion. For those kind of constraints, we can actually solve our LPs. We'll call them SDPs because of the structure of a matrix we have on Y. Okay, so now I'll use the third characterization of SDPs of a PSD matrix, which is that you can always write it as a product of two matrices like this. So let's do that. Okay, so what is the Yij entry of this product? It's just YUV entry. It is just the inner product of the W vector, right? I mean the UVth entry of this is just the Uth row multiplied with the Vth column, right? That is just WU inner product WV. Note that this is very similar to the constraint YUV equals to XU which started this whole thing off, right? But now instead of XU being numbers, we have said that instead of XU we have WUs which are vectors. So indeed, if these vectors somehow were one dimensional by luck, then this would be an exactly capture the problem, right? Exactly capture this constraint. But in general, these could be any high dimensional vectors. So I'll just write the SDP again. Okay. Notice that we had XU XV. Instead of that, now we have WU inner product WV, some vectors, right? And we had the constraint that XU square is equals to 1. Instead of that, we have a constraint that norm of WU square equals to 1. Okay. And we had so these WUs are some n-dimensional vectors, and this is what is called the vector programming formulation for this problem. Okay, there are some subtleties here. We'll skip those.
Okay. When you write this Wi belongs to R, that means a whole W1, W2, Wn. You're saying it should be a single vector. What it means if you take the semi-definite programming, like Y should be semi-definite, and it's like rank of Y equal to 1.
Exactly. So that was going to be my last point. You should read about this. So this is really a rank constraint SDP. That's why we cannot add this constraint. Okay. Because rank constraint SDPs are not convex. You can't solve them. So yeah, if we want to insist on Wi equals to 1, that would be equivalent to adding in this not in this previous construction where we had the constraint that Y is PSD. It would be equivalent to adding the constraint that the rank of Y is 1, which we can't add.
I guess what you were saying is this really looks like the quadratic program, except everything is a vector and the products are inner products, right? In this.
Yeah. But his question was something else. His question was like this is like rank 1 constraint, which is true, which is another way to see this, which is what I assign as a reading exercise for you guys. Okay, right. So now I think we have the inequalities in the right direction. SDP opt is greater than equals to opt. So we're calling this LP opt. Instead of that, I'll just call it SDP opt because that is exactly what the definition of SDP is. Great, we have this vector program and we have around 10 minutes to analyze this. So let's try to see. Sorry, is it 12:30, right?
So we have 12:50.
12:50. Okay, we have 15-20 minutes. Okay, we'll see. Okay. So maybe maybe there are some parts. But what I want to say is okay, then I have some time. I can maybe try to motivate this more. Okay. So maybe what I was trying to do is like a very methodological way of doing this, but there is another way to interpret this. Like you could have directly jumped to this. I could have started the talk with this specific program. Okay. How do we do that? Okay. Recall this is exactly what I wrote at the start, right? We wrote this LP, right? We had 1 minus XU XV, right? Then we had the constraint that XUU is equals to 1, and we had the constraint that YUB equals to YUBU. That is fine. right? We had all these constraints. I could have directly said to you, okay, that what do we do in a linear program? We say that okay, relax xu to be from being a 0 1 to being a number between 0 and 1, to being a real number between 0 and 1. Okay, what instead if I say, instead of relaxing xu, the constraint that xu is 0 1, to say that relax it to be a vector instead of a number between 0 and 1, in this case it will be a number between -1 and 1, I say you relax it to be a vector in Rn. Okay, then really what you would have is, instead of 1 minus xu xv, you would have 1 minus wu inner product wv, and xu square equals to 1 would actually mean this constraint, and I really mean to relax it to an n-dimensional vector. Now if I directly say that to you, it is not at all clear why this weird thing which I am calling a vector program is solvable at all. Okay, but we have seen this connection, right, which actually that is why this is solvable. But you might have actually, for the purpose of analyzing the algorithm I am going to discuss, you could have directly said, okay, whatever we do, like mostly how do we analyze LPs or anything is in approximation algorithm, we try to relax them. Okay, if there are xu's or some 0 1 numbers, we try to relax them to a number between 0 and 1. We might as well as ask, like, let us try to relax xu's as a vector in Rn, and that would give us this program directly. Okay. Right. So what is this program trying to do? Okay. Let us try to, this is going to assign some vectors in Rn, right? We have some constraints on the vectors, and the objective function is trying to do something with the vectors. Okay. So if you really think about the graph, okay, this is maximizing. Again, this summation is missing, but that's fine. We're used to that by now. So what is it really trying to do? If you think of single edge UV, right? Yeah. So what does this constraint mean? This constraint means that the vectors are unit length. If I center them at an origin, the vectors all lie on the boundary of a unit sphere, right? And what is this constraint trying to do then? There is a maximizing. There is a max function here. So what is this constraint trying to do?
It's trying to find orthogonal vectors.
Well, not really orthogonal, because so it's trying to like trying to maximize thing, right? So we try to minimize this. And how do you minimize? Of course, you can try to make it 0, but you can try to do even better, right? You can try to make it even opposite to each other, right? So in fact, this is what it is actually trying to do. This is trying to embed the graph into an n-dimensional sphere, where it's trying to pull apart the vectors corresponding to an edge far away from each other. Does that make sense? Okay. So yeah. So this is what this vector program is trying to do. And the point is, we already said earlier that this is at least, the value is at least opt. Okay. But how do we round it to get us actually a solution from this? Okay. So far we have seen that, okay, if xu, for example, if we discuss the vertex cover problem, if xu is a number between 0 and 1, we do this rounding, right? If it is greater than half, we round it to 1, and we have seen similar roundings in other lectures in the school. But now we really have vectors, right? So what should we do? How do we round this to get a... So eventually we want plus minus 1 number labels, right? And those should indicate the cut, right? How do we get a cut from these vectors? Okay, so how do we run this? Well, if you look at this picture, the vector program was trying to pull the edges apart from each other. If you look at this objective, right? How does it make W inner product small? It tries to make it as far away from each other, right? So the edges of the graph, if the optimizer has done a good job, okay, this vector programming optimizer has done a good job, it would have tried to pull the vertices, the vectors far apart from each other, right? In which case, you might imagine an hyperplane like this, okay, which goes through the origin, okay, it would end up separating a lot of edges in the graph, right? But how do we choose such an hyperplane? That is the question. Let's see. Okay, so notice that there are a few properties we can say we need from this hyperplane. For example, we want. For example, what we want, finally we want a label plus minus 1, right? So we have n-dimensional vector and we want a real number finally, right? And while this n-dimensional vectors carried a lot of information, for example, it carried information that this edge these vectors are far apart from each other, so their inner product is small, like they're far apart from each other, right? So we want to retain that information about the inner products, whatever information we can retain, okay? And also in some sense this stacking property you can ignore for now. So we want to retain some information about the inner products while still getting numbers from these vectors, okay? Because eventually we want a plus minus 1 kind of a thing, as we do always, right? So in fact this is a question we can ask independent of even this max cut problem, okay? Which is, what is the best one-dimensional map for example, let us say you have a data point in Rn, okay? And you only want to store one number per data point, okay? What is the best way to do that? Is data, compress the data, dimension reduction or something you want to do. But what is the best way to, best 1D map? Best in a particular sense, I'll make that sense precise. But what do you think is a good idea to, like, exactly, Johnson-Lindström does it for dimension D. But like you can even think more fundamentally what you would want to do to preserve a data point. Like what does JLM, like what does Johnson-Lindström do under the hoods? Like, or like even if you have not seen Johnson-Lindström, what would be the best map to preserve a data point? Sorry?
You take a random map according to some Gaussian distribution and
exactly. It may sound weird if you haven't seen this, but actually this is the best map. Okay, choose a random direction G, okay, and take the inner product of this data point with that vector. And this is an exercise for you. You can show that in expectation, this is what is called an unbiased estimator. In the sense that in expectation, it preserves at least the length of the vector. It retains some information about the vector. If you do this, okay. Random Gaussian direction, yeah. I'll define what that is in a second. Yeah. Okay. Yeah.
That exercise is only true for Gaussian direction, not just
yes. So if you do this, if you want to do this, like you can also ask the question if I'm happy, like what is the best 2D map, right? Then you should really take two Gaussians. Sorry, is there a question? Wait. Yeah. So the best 2D map would be to take two Gaussians, and you can show more properties about that. We'll not getting into this what this gentleman called the Johnson-Lindström lemma land. Will not go there, but this is just to derive some intuition that this is indeed true. So yeah. So how do we choose? So firstly, the question there was how do we choose a random direction? I'll probably skip this part of the talk. The point is you can just sample independent Gaussians and you can show that this is the final term here only depends upon the norm of the vector. It doesn't depend upon the direction. This is direction independent, what we call as a rotationally spherically symmetric thing, and it can be done. So how do we choose a random direction? We just take n independent Gaussian random variables and just put them together in a vector. That is a uniformly random vector. We can show that. Right. So now we wanted these vectors were in Rn, right? And these vectors really tried to capture some information about the graph. That if the graph there is an edge, that these vectors were like the SDP tried to pull apart these vectors, right? If there was an edge in the graph, so there is some information of some edge information in these vectors, right? And now we want to round them to numbers. So given what we saw in the previous slide, what do you think would be a good idea to get numbers out of these vectors? See the question? Like the vector programming or the SDP gives you vectors in Rn, right? Those vectors, the inner product of them, for example, they are far apart for an edge. So the fact that they are far apart is being captured by the fact there is an edge is being captured by the fact that those vectors are far apart in the optimal solution to the SDP. Okay. Now I don't know how to route. Like I finally want +1 -1 labels, right? That is the cut. So how do I get +1 -1 labels from this? Oh, I think I already gave the answer. The answer is to choose a random hyperplane. Okay, random again means, so how do you choose a random hyperplane? Well, if you choose a random vector that fixes the hyperplane, right? And we just saw how we choose a random vector, right? Just put n Gaussians together, right? Yeah, and this is the Gormans-Williamson algorithm that gives 0.878 approximation algorithm. Okay, you solve the SDP, obtain the vectors, Okay, choose a random and choose a random direction the way we defined. Let's just take n random Gaussian variables. Okay, and the rounding, how do you get plus 1 minus 1 from them is okay. If this is similar to what we were doing earlier. Now recall the variables are minus 1 1, right? What would we do for vertex cover? It's greater than half, we put it to 1. What should we do now? With minus 1 1, if it's greater than 0, we should put it to 1, right? That's exactly what this is doing, the sign function is doing. It looks at the sign. If it's a positive number, it gives 1. And this is the set S we define, and yeah. So another point is, this is the main theorem, okay, that this particular cut in expectation gives at least 0.878 times the optimal value. Okay. So indeed we have we will improve from half. And yeah, let's try to, yeah, maybe, yeah. Are there any questions?
How do we choose n to be?
How do we choose?
Like what do we choose n to be? The dimension of the
That's a very good question. That is what I earlier talked about this. Yeah. Okay, maybe I'll not go that back. The point is we need to have. Sorry, the question was small n, right?
small n.
Yeah. So the small n is the number of vertices in the graph. You probably need to ask how many dimensions the dimension of the vector, like w1, w2, right? That also needs to be at least n. Otherwise, this is not a convex problem. Did I get your question right? Yeah. So now, like similar to what we were doing in Professor Prajakta's class, we were trying to do this showing that what is the probability that an edge UV is cut in a graph, okay? And that looks like a difficult n-dimensional calculation at the very outset. But the main point is that it isn't an n-dimensional calculation. All that matters is the 2D plane that contains the vectors. Because see, we're trying to slice a sphere, right? The only thing that matters whether an edge u or v will be separated is the angle between them. Okay? If the plane goes through them, okay, and the plane really is this thing, and this is the normal of this plane. Doesn't look like a normal, but yeah, this is intended to be the normal of this. And if in this case, this plane doesn't separate these two vertices, right? And we can analyze this probability, okay, using simple. Okay, we're just writing it out, like what is the probability that edge is cut? We just look at the algorithm. When is the edge cut? If these signs are opposite, right? If these signs of a vertex u and vertex v are opposite, then the edge is cut. We just write that out, and it's like, yeah, ignore the calculation. All you can see is when will an edge be cut if it passes through these, right? If the plane passes through this, if the random hyperplane, if we try to rotate this, it passes through this. Right? And what is the probability of that happening? It was a truly random hyperplane. So the probability is that, in this plane, the angle between these two vertices were theta uv. Then the probability is theta uv divided by pi. Right? If you just take a random hyperplane, random line, sweep it through this, what is the probability that it separates these two? Right? That probability is theta uv by pi. Okay. Yeah, there's some. Ignore this part. But on the other hand, notice that SDP has, for this particular edge UV, SDP had this thing in its objective, right? For an edge UV. Okay? And these are linear constraints, so this is actually 1 minus cos of theta UV. In the previous calculation, we have theta UV, and the SDP opt is 1 minus cos of theta UV. This is a question, Arka.
The question is like how, like, could you go, so the probability calculation that you're showing, W transpose, GG transpose, W, from that, how do you write the next line?
Yeah, because GG transpose is the identity matrix.
But,
because they are independent Gaussians.
No, but W and WU and WV are like, they are not random variables. Right?
They are not random variables.
That probability then, like, doesn't,
yeah.
What's the probability space?
I see. I see. The probability is over. Yeah, that's a good point. Yeah.
I guess just a middle line can be removed.
Yeah. Maybe we need to do it more formally. Yeah. Good point. Yeah. Okay, but for now, okay, maybe ignore the calculation. Just look at the intuition that the angle between them is theta uv. A random hyperplane cuts them with probability theta uv by pi. Okay, and what is the SDP value for this edge? For this calculation, we just calculated that. That is 1 minus, these are 1, so 1 minus cos theta uv by 2. Okay, and now we just relate these two, and the analysis is actually the same as we did for the half approximation. We just apply linearity of expectation, or this is an edge by edge analysis. Okay, we analyze it for one particular edge. Okay, we'll analyze it for, so we write it out. Firstly, the expected value of the algorithm summation over this thing. Okay, and we can write it like, this is just some fancy way to write it. I mean, I'm just writing out what these calculations were. There's nothing fancy about this. Notice that this summation is SDP opt, and there is some weird function of, so this is a summation over all edges, right? The only thing I noticed that instead of doing this weird calculation for all edges, I can take the minimum value possible for this function, and I can always write this inequality. I take the minimum value for this function, I pull it out, I can just write it this inequality. And what is the minimum value possible for this function? Well, these are two functions, one by pi r cos rho, and these are some two functions, and you want to make the, so the numerator is the numerator is the blue line and the denominator is the red line. Okay, and you want to minimize this, so you want to pick the smallest value of the blue line and the largest value of the red line, which comes out to be these numbers. Okay, and that is where you get 0.878 from. The ratio of 0.74 to 0.84, that is 0.878. Yeah, I understand that, and this constant, this looks like a weird constant, but it has its own name. It's called Gormans-Williamson constant. Note that this is an edge by edge analysis. I really pulled out, I really was supposed to do this calculation for every edge. I just said I'll take the minimum value and I'll pull it out. This is sometimes very helpful when you want to analyze SDP. That this is an edge by edge analysis. In fact, you'll see more SDPs in the tutorial session. You'll see one more SDP that is also analyzed using this. And now you would want to ask the question, where is weird number 0.878 coming from? Is it the best possible? Okay, and up to some quantifiers, it is indeed the, I'll wind up. So for example, you can take a simple triangle graph. We saw this earlier. Okay, here you can actually construct vectors where this thing is 9 by 4. SDP opt is at least 9 by 4, and the integrality gap is 0.889, very close to what we had, 0.878. In fact, if you take a 5 cycle, you can get it to even better. You can get it to be 0.884. Okay, and I'll just wind up here. And finally, it was showed that the integrality gap is actually exactly alpha GW for this SDP, exactly that same constant. So what that means is that for this analysis, with this SDP cannot be improved to get better than 0.878. But you may, okay, I'll skip this viewpoint. Okay, so what is the status of the max-cut problem? Okay, so we just showed an alpha GW approximation. You may ask, is that optimal? Well, assuming there is some conjecture called the unique games conjecture, okay, which Professor Akash may talk about it, I'm not sure. But assuming that conjecture, this is indeed the optimal thing you can do. So this weird number alpha GW at first may look very weird, but this is indeed the best you can do. There are ways to improve it. One point I want to just mention is, spectral methods can, so we earlier talked about the failure of linear programming, right, to capture better than half. Spectral methods can indeed get better than half, it is known. They can, it's not whether they can go to 0.878 exactly, okay. So it really seems to be something about these eigenvalue computations. So for example, this SDP, what is the power of this SDP over this LP? In some sense, we have built in some eigenvalue computations in LP, right? So that is what I said, LP plus a power allowed to it. That power is really this eigenvalue computation. And those, in some sense, really help, because even without writing an SDP, just using spectral methods, which again Professor Akash will talk about tomorrow. We'll not talk about this 0.61, but he will talk about something related to this. So those can actually improve 0.5. Right. Maybe I'll skip all this. So the main the takeaway is that SDPs are really powerful. They achieve the state-of-the-art guarantees for many problems. You saw one problem X-cut. We'll see another problem in the tutorial session today. Tomorrow we'll see another problem where SDPs are achieve the state-of-the-art guarantees. The other takeaway was we can really solve these huge LPs by separation oracle. And these powers of this SDP is still an active area of research. This is the paper that really started this SDP analysis in algorithm, and this is not a too old paper. Still active area of research, and still the full power and limitations of these SDPs are yet to be understood. Still an active area of research. With that, I'll stop.
Okay, questions? Since there are no questions, let's thank Ramesh. So I understand this was a lot. So we'll have more guided exercises for SDPs. Like you should actually do them and try to figure out some of it. SDPs in one session is almost impossible task, I feel. So yeah. I encourage you to actually go through the exercises, and there are no tutorial sessions today. You might have.
Oh, okay. I didn't know that. Yeah.
Yes. So there is lunch outside. Then meet again at 2:15. Yeah.
Do you need to close this?
Let it be there.
Okay. If you want to formulate this integer linear programs in form of quadratic programs, then why don't we with identities or empty factors or the stupid are also stupid are also not all cases. For example, if you consider these lower and white programs, then TDP you have to run it quadratic what kind of fun is that?